All right, welcome back, everyone. Yesterday, we kind of left off with discussion of racking components, and we saw that the systems consist of flashed L feet with rail and then a clipping system that fits into this top channel of rail that kind of clamps the modules down onto the rail. And that's pretty generic for every kind of racking structure. Even if you have some kind of unconventional racking structure where you're not using the rail, but you're using the solar modules to just directly, you still have this kind of flashed L-foot attachment. It's a pretty universal piece as far as solar goes. And so we started to look into, how do you go from an array layout to a final design? And for that, your manufacturers want to make it as easy as possible for you to design systems using their products. So racking manufacturers and inverter manufacturers have sizing softwares for their products available on their website that, once you know what module you're using and what racking you're using, you get your final array layout, go to the website, run the configurator, and it develops a balance of system racking material for you. So let's take a look at that. Here we have our array layout. We've rebuilt it in this particular racking software. And what the software is doing is it's walking us through our site conditions. So what is your 3-second wind speed? What's your snow load? And also exposure category. If your array is right near a bunch of homes and a bunch of trees, it's going to get less wind loading than if it's on, say, a flat plain. And we talked about nuances of rail span, and it's kind of interesting. If you use thicker rail spans, your attachment feet can get further and further apart, but also you're using more aluminum in the rail material. So the thicker gauge rail costs more. My preference is to use thinner gauge rail and put that cost into the attachments rather than the rail itself. And so, going with a thinner gauge rail and doing 4-foot on center attachments provides a very good distribution of loading across the roof truss. And then sometimes the attachments have to be even closer together. But what we can see here in this picture, this is a well-installed racking system. We can see kind of 4-foot on center attachment points, but then they're also staggered so that every single rafter is getting that load spread throughout the array. And then there's some stiffening and load distribution effects by running this rail and then attaching it to each rafter system. Now we can also see at the corners of the array, here they're doing a 2-foot on center instead of a 4-foot on center, and that's basically so that they can achieve this kind of staggered effect. But what we also see is up here and down here they've put the attachment points 2-foot on center instead of 4-foot on center, and so what that does is it gives the corners of the array, which experience a little bit higher wind loading, a little bit more support. And then lastly, we talked about how in areas of heavy snow, you might also want to go and put additional attachment points along the bottom rail, because what happens is if you're in an area of heavy snow, all of the weight of the array starts to transfer onto this bottom rail, and all the weight of the snow on top. And so in areas of heavy snow, particularly on a retrofit, older roof, in some cases that weight can cause the attachments to break through, maybe not the rafter, but it might push the rafter down enough to break through the cladding. So you want to be aware of that. And then there's also reasons not to go all the way to the edge. In our racking, we saw zone 1, zone 2, and zone 3. And essentially zone 3 is corners of the building, whereas zone 1 would be in the interior of the building. And so it's not a bad idea not to go all the way to the edge. For one, staying 3 feet off the sides is going to keep you compliant for most zoning restrictions. Sometimes in New York or on flat roof row homes, it might be a 4 foot offset. And if you have the space for a 4 foot offset, I would do it because it just means your working space up on the rooftop is just much more accessible. And so if you're doing remote design work where you're just dimensioning out the rooftop, say with a software like Google Earth, you don't want to be so aggressive with your design that if you miss anything, if you miss a dimension, having some wiggle room does help. Now, yesterday we talked about a conversation I had with a racking manufacturer who said they could provide an engineering stamp in any state for their racking system. But what the racking companies look at is the integrity of their racking. They don't know anything about your roof that you're attaching it to. And that is where that's more important. I kind of trust that a solar manufacturer is going to sell me a quality racking system that'll hold up to the design requirements. But what we can, this is a racking software, and this one is Iron Ridge. So Iron Ridge, and I am not, I don't care about what module I use. I do have inverter preferences. Racking to me is very generic, so there are maybe some small nuances that an installer would prefer, as if they're installing the racking system over and over and over again. But if it's for a one-off project, picking out which racking system I'm using is the least of my concerns. But I do like using Iron Ridge, even though I don't think they're necessarily the best racking system as an installer. As a designer, what I really like about Iron Ridge is they actually give you, based off your array layout and point load locations, the uplift and lateral and downward forces that wind and the weight of the array will have on the truss. And so, normally this kind of information is not provided by the racking company. And then that, if I prepare a scope for a structural engineer, it's a lot cheaper if I can say, these are where all the attachments are, and these are the forces on each attachment, rather than asking the structural engineer to come up with that calculation. But you also get things like the weight of the array, and what we can see is that solar on a rooftop is going to add about 3 pounds a square foot of dead weight onto the roof. But what we'll see is that the forces, I guess we won't see this, but the forces on each attachment will distribute this weight. And so effectively, the more attachments you have, the better that force is distributed over the roof truss. And your solar installer may not want to do 4 foot on center. They may look at their racking and say, oh, it's rated for 6 foot or rated for 8 foot. But what they don't realize is that these forces could substantially increase the fewer attachments you have. So more attachments is better than fewer attachments, even though you're putting more holes in the rooftop. Remember, it's really not the solar attachment that's going to leak. It's the pre-existing attachment penetrations that are surrounding the array that, in my experience, become the leaky points afterwards. A comp shingle rooftop is really not intended to be a retrofit construction work site. So there's always going to be some imperfections in a retrofit process. All right, so moving on, here's finally from our array layout and site information, we get a list of all of the components that we need for our racking system, and that will include things like your flashing and your clips, but it'll also include grounding clamps for connecting the rack to your system ground. The clips that clamp the module down onto the rack are usually listed as a ground path. And so, generally you just go and land your ground onto a ground lug, and then the array becomes grounded throughout. You might get splices if you need to splice rails together. We see some grounding straps. And then, you would also specify, hey, I'm using microinverters, or hey, I'm using DC optimizers, which we'll get to in a minute. And it'll give you additional hardware for that. And again, I usually will go and take this final balance of system material, and if there's one item that I'm going to have extra of, I'm going to get more of these T-bolts, because those are really easy to drop off the rooftop. And if you lose one, you can use a hex bolt, but you have to slide it all the way down from the end of the racking. And depending where you are with your cable management and attachments and install, that might not be an option. So it's always good to get a few extra T-bolts and maybe tape them to the inside of the inverter or something, so that if someone's servicing the array down the road, they have a little bit of the specialty hardware on hand. All right, so inverter selection. We just mentioned DC optimizers and microinverters. When we did Half Moon's commercial array, we wanted to use the electrician who was responsible for the rest of the electrical system of the building. We didn't want to have two contractors involved. We wanted the one local contractor. And in Wisconsin, they don't have a huge solar industry. This was actually the first commercial solar array in Eau Claire, Wisconsin. And we used microinverters, even though they're kind of the most expensive option, because they're so simple to install. And so the installation was a breeze. The microinverters are very much a plug and play system. The problem with microinverters is that now, instead of having one inverter for the entire system, you have dozens of inverters for the entire system. And while that adds simplicity, and you get like module level monitoring and module level optimization, which is really good for mitigating shade. So there are clear advantages to using these like module level panel electronics, which is sometimes spelled out as an acronym of MLPE. But the problem is these things have so many benefits to the consumer. Hey, don't you want to see what every single module on the rooftop is doing? Don't you want an easy installation process? Can't those values overcome the cost increase of the microinverter? And I have made those arguments in past solar programs of years past. But as I get more into aging solar arrays, what happens is, out of all of your racking modules and inverters, the inverter is the number one component that is going to fail out of those three. And so if one microinverter fails, you kind of have to, if this microinverter were to fail, and now we have solar modules on top of it. So here's a solar module, here's a solar module. I guess one of the rails is not pictured. Here's a solar module. If I have to, and it's surrounded, if I have to go and service that one module in the middle of the array because its microinverter has gone on the blink, I have to get up on the roof. Maybe I'll start up here, and then I'll have to unclip this solar module and set it aside, and then walk down, and then unclip this solar module and set it aside and walk down, and then detach the microinverter and remove it and deal with the warranty process. And it's like, wow, I'm doing like 5 hours of work to replace a $50 to $90 part. So it's a huge out of whack balance of labor versus the part. And then, one single solar module is only going to be saving you, $50 a year. So it puts you into this kind of very difficult position of, well, do I replace the microinverter, but if I'm billing for that maintenance task, the bill is going to end up to be larger than the rest of the value of that module that I'm replacing. And so the problem with these microinverters is, on the one hand, a microinverter could go completely offline and the rest of the system remains productive. But servicing that microinverter becomes a very expensive and costly task. And my solution is to tell the customers, look, we're not going to replace a single microinverter. We'll have to wait until 4, 5, 6 of them fail before it's worth anybody's while to go out and maintain it. And while that might make sense on paper, I've never met a client who is satisfied with 98% of their array working. They're going to get an error message in their email saying that this microinverter is offline, and they're going to want it fixed. They want to see 100%. And so sometimes this level of granularity, while it does have some advantages in terms of operability of the array, it can result in increased maintenance costs. And so many of the solar installers, and myself included in this, we've kind of come full circle on this roof-mounted module stuff. It came to market as a shade solution. So if a portion of the array is shaded, the rest of the array remains unaffected. And hey, that's a great application. If you have any sort of shade on your job site caused by, and really east-west shadows, like dormers, chimneys, a tree line, microinverters or DC optimizers, module level panel electronics, you kind of have to use them and bite the bullet and just take it. But if I have a completely unshaded rooftop like Half Moons, in the past you might say, oh, I'm going to use this stuff to do simplicity of the installation, but it will add more complications for maintenance. Now, another advantage of these module level panel electronics is when the power goes out, the power is killed right up on the rooftop. There's a danger in kind of old school one inverter for the entire system is you're taking all your power cables and then running it off the side of the rooftop. And if the power goes out, this cable remains energized. And that can be a problem if the power goes out because your building's on fire and the firemen have pulled the plug to your power and they want to go into the building to rescue people. They're concerned about those live solar wires, and being able to kill the power up on the rooftop has actually been incorporated into National Electric Code. So now there's almost a mandate by National Electric Code to de-energize the solar array up on the rooftop, and your microinverters or DC optimizers will add that functionality right out of the box. And so you have a couple of options when you're designing a roof mount array. You can use microinverters where the whole solar system is up on the rooftop. You can literally just go and run a microinverter circuit down to your electric service panel and land on a 20 amp breaker. And there's code considerations involved, but it's there's no inverter on the side of the building. It's all up on the rooftop. Or you can have string inverters, which is one inverter for the entire system. And the problem is that home run cable can remain energized, and also you don't get if this part of the array is shaded, it's going to drag down the power output of that entire circuit. And then on top of that, when you add multiple circuits to the string inverter, and you have these circuits at different power levels, the inverter gets confused and says, well, how do I track my energy? Because this shade is causing the voltage to jump up and down on that circuit, and it gets the inverter confused. Not a real problem if you don't have shade on your array, but what that means is without these module level panel electronics, a shaded array has very little production. And so then we had another market entrant called DC optimizers. And they say, look, we know that buying one inverter instead of dozens of inverters is going to be cheaper. And the inverter is a commonly serviced piece of equipment, so we don't necessarily want it up on the rooftop underneath the solar array. So let's go and still have our DC to AC inverter up on the on the side of the building, but up on the rooftop we're going to do a DC to DC converter. And what that will do is it'll take the output of the array and step it up to as high up as it can go. So there's a 600 volt limit in National Electric Code for residential rooftop arrays. And so what we're going to do is step the voltage up of the system all the way up to 550 or 590 volts. And when you increase the voltage, you decrease the amperage. And what that allows is this DC optimizer system to have a lot more modules on a given circuit than without them. And so with the DC optimizers, you can do larger circuits. It's a lower cost option than the microinverters. And then some of your failure is mitigated by being down on the ground. And so this is a very popular option. It's probably the most popular option for rooftop solar, non-large scale commercial, residential, small commercial. The DC optimizer system is quite popular. Now, if you want to use a string inverter and you don't like the idea of all this roof mounted stuff, there's a new product on the market called a rapid shutdown combiner box. And I think we're going to get into that in just a minute. So, it used to be that string inverters were really bad for shade, and so you would have to use microinverters or DC optimizers for shade. Then the de-energizing the array on the roof requirement came to code in 2014, and it's since been expanded in 2017. So now what National Electric Code says is you have a 1 foot perimeter around the array. And that applies to subarray sections too. So if I have a subarray over here and a subarray over here, and there's more than 2 feet of distance between the subarrays, then this little jumper has to de-energize too. And you really can't do that without module level panel electronics. But if your array was one big rectangle and there weren't long jumpers in between, instead of using module level panel electronics on every single module, instead you can get rid of that and just put your rapid shutdown disconnect in your pull box where you would go into the attic. And so now you can get these junction boxes or pull boxes with a circuit that uses the neutral wire as a relay. So you run a neutral wire, even though it's a DC system up on the rooftop with no neutral, you still run a neutral wire up to the rooftop. And when the power goes out, that triggers a disconnect switch to open up and de-energize the array. So when I do my arrays, I've moved back into string inverters and doing rapid shutdown combiner boxes, simply because it's fewer parts. And because it's fewer parts, there's going to be less failure. Because there's less failure, that's less maintenance on my end, more satisfied customers. It's kind of interesting, back in the day when solar was kind of dumb and you just had string inverters, and these string inverters were not the best at detecting maybe not a ground fault where the electricity is faulting to ground, but they weren't good at detecting another kind of fault called an arc fault, where it's just, maybe you have a connector that's not firmly made, and it's firmly made enough to transfer electricity, but it's jumping over some air and there's some resistance in that. It might be just be dragging down your production a little bit. It's still an error. It should be fixed, but the old school inverters couldn't detect that. And so, solar developed this reputation of, oh man, it's a miracle technology where you can just install it, plug it in, and you'll never have any maintenance events ever again. What's funny is as the module level panel electronics come to market, definitely a lot of customers want them because they like seeing what every single module on the rooftop is producing. But from a fleet management perspective, sometimes you get a lot of questions of, well, why is this one module not producing when all the others are more productive? And it could be that, well, it's within the tolerance of the module, it's still within the warranty. Maybe there's some bird poop up on the solar array, but you just deal with a higher degree of customer dissatisfaction because they can see all the blemishes in your production. They don't just see one monitor that shows the total system output. And whether or not that's something you want to give your customers as a value, or kind of take the Apple solution and have a less functional but more satisfactory solar ownership experience, that's more of the route that I would take. Um, the string inverters of years past only had one power point tracker. So you have a string inverter, and maybe you have 3 circuits of solar panels. But those circuits would be combined before they hit the inverter. So you'd actually only have one cable coming into the inverter. Many inverters nowadays, and especially the higher end quality inverters that you're going to want to use, nowadays the string inverters have taken a note from these microinverters and DC optimizers, and the more expensive string inverters have more stuff in them, so that these 3 circuits of modules could actually be individually landed on the inverter, and they track every circuit independently. So now a shaded circuit would still take down that one circuit, but it wouldn't take down the others. It wouldn't confuse the inverter on a partly cloudy day into shutting down and triggering its 5-minute restart. So I guess what I'm trying to say is the string inverters made today are much more shade tolerant than they were 5 years ago. 5 years ago, a small amount, just one little shadow on one module could throw your whole system into haywire. But now your string inverters will often have 1, 2, or 3 circuits that they can track independently to provide some degree of mitigation. And so at that point, what you would do is you'd land all 3 circuits in a junction box, and then that junction box would take care of your rapid shutdown. And then instead of combining, your 3 circuits would go straight through and land on your inverter, where they're individually managed by the inverter. And that means there's 3 times as much stuff on the DC side of that inverter than there used to be. And so inverter pricing, especially on the high-end quality inverters, you get what you pay for. If you're trying to choose between if you need to go cheap and you have an unshaded solar array, you don't really need multiple PowerPoint tracking and stuff like that. But especially shadows in the early morning or late evening, they can get quite long. And if you have some shade mitigation, you will get a performance boost out of your system. So, rapid shutdown combiner boxes have now been on the market for a few years. So you're not being a guinea pig if you want to go back to string inverters and start using rapid shutdown boxes. So what I like to do is I like to hide these junction boxes underneath the array. And the reason that I do that is that way, the racking has a cantilever, and so your last attachment might be hidden underneath the array here, and then your rail kind of cantilevers, and your last clip goes at the end of the rail. And so you can barely see that clip at the end of the rail. And so your rail will end right at the edge of the array. All of your cabling is underneath the array. If you can land your junction box underneath the array and go into an internal conduit run, you achieve this nice kind of hovering effect where you don't see any cables or conduit or wires, and it looks good. Now, I do have to warn you that most of the electrical junction boxes that you get at your local hardware store are about 4 inches deep. But by the time you get into your solar, by the time you get to your flashed L-foot and then your rail, and then you get to the module frame, which gives you a little bit more, about 1 inch of additional depth. This rail's about 2.5 inches. There's about a half an inch here, and then you get 1 inch from your solar module. That's about 4 inches. And so what that means is by the time you get to putting in the hole in the roof where the cables will go down through, you can kind of see our flashed pipe boot kind of hidden underneath this box right here. But generally, if you want to do a nice hidden internal conduit run, you cannot use a box from Home Depot, Lowe's, or Menards because it won't fit underneath the array. So, when you're ordering your specialty material, you'll have to, this is a very popular box called a Soladeck. It's actually made in the same town where Half Moon is located. And that's well, you can see it's a lower profile box with integrated flashing, and that's kind of the more professional product. The disconnects, or if you have overcurrent protection because you're combining circuits together up on the rooftop, they do not need to be readily accessible. So you can hide them underneath the array. Some jurisdictions don't allow it, but I've never run into a problem with that. Now, back on the microinverter, DC optimizer, string inverter discussion, I like to show this timeline of inverter adoption because microinverters and DC optimizers are still relatively new compared to string inverters. So back in 2010 is when Enphase kind of came to market. And so before then, it was really SMA, very high quality European string inverter. And then the rest of the market or inverters from the United States that all came from a company called Trace. So they were Trace and Xantrex and Schneider is now involved in that. And then they're all competitors. But SMA back in the day was like the quality leader. If you wanted a good environmental rated inverter, SMA was how you would go. It was funny. The SMA inverter was not as efficient as some of the other string inverters on the market. And the reason is the SMA inverter does not have a fan inside of it. It's passive cooling. So it just sits there and radiates heat. Whereas other inverters will put a fan inside the inverter and force that air through the inverter, and that cools the inverter down and boosts the efficiency. But then again, the problem is that the fan fails. And when the fan fails, the temperature in that inverter rises and it triggers the alarm and turns the inverter off. And so, are you going to put a part into your design that's going to boost your production value by 0.5%? If it's cheaper and more efficient, you might say, well, of course I'm going to do that. But you have to remember there's no free lunch here. I did a lot of solar arrays in Texas, very hot in Texas. It's crazy. You drive across the Texas border and your thermostat just climbs and climbs and climbs. They spin those little fans inside the inverter around and round and round, pretty much 8 hours a day, 11 and a half months out of the year. For that, I'd much rather have a passive cooling system that's not going to fail on me. Anyway, Enphase came to the market, and what it really did is grew the market, because now all of a sudden the customers who had shaded rooftops that were subject to partial shade, maybe most of your solar production is going to occur between 10:30 and 2 or 10 and 2. So, having a shaded roof until 9 is not the worst thing in the world. Maybe you'd have a tree line that would just climb up your rooftop for 2 weeks around winter solstice. And, having the bottom row of modules shaded for 2 weeks on winter solstice is not the worst thing in the world, but if it impacts the entire array, that might be the decision between only having a 4 kilowatt system or an 8 kilowatt system. So what microinverters did was, by providing shade mitigation, they enabled rooftop surfaces to be used that were previously ineligible for good quality solar production. So we can see Enphase came to market, and their market share, they just went on a tear. Well, then they got some competition with SolarEdge, which does the DC optimizers. And what we can see is the less expensive, better failure mitigation, but same module level optimization value. All of that added up to say, if you're a solar installer, maybe the Enphase microinverter system is a little bit easier to install, but you're going to go after the cost savings of the otherwise equivalent or perhaps better system. I would still absolutely recommend microinverters for do-it-yourselfers who are not very comfortable doing electrical work. It's the most plug-and-play system, but it isn't without its detriments. If I'm using a professional installer, I'd probably want them to not use microinverters, but to go with a DC optimizer system if I wanted that module level performance. And of course, my preference is for string inverters and smart combiners, which are actually easier to install, but you have to kind of know what you're doing, because the combiner box is not part of the inverter system in many circumstances. It's supplied by a third party, and so you just have to do a little bit of if you're a solar installer, you might not be thinking about running a neutral up to the rooftop. And so transitioning into smart combiners, you have to kind of adjust your design process a little bit. But if it was for my personal array, I would want to do a string inverter with multiple power point tracking and just get rid of this roof mounted stuff. I've been taking on a lot more residential project work lately, and the developer I work with, they insist on using the DC optimizer system. And I dislike that, because it adds a good day to my install time, because I can't just put the racking up and then the modules up. I have to put the racking up, and I have to look at where these optimizers will land, because they have to be under the module. You can't put the module frame on top of the optimizer, or it won't be even. And so now I'm looking at where the module frames are going to be, where the optimizers are going to be, and then you still have to do cable management. And if you're just doing tie wraps around your rail, now your module frames have to avoid the optimizers and the tie wraps and your L-feed attachment. And it just, there's a little bit more finagling to be done up on the roof. It's something that seasoned solar installers deal with on a regular routine basis. I like using kind of new to solar electricians on the install. So I'm looking for something where the install itself is a little bit simpler, provided that there's someone who knows what they're doing on site. If you're just doing your own solar array, microinverters are great. I taught a Half Moon class live a few months back, and audience member had actually taken 2 of my solar classes over a course of a few years, and he brought in pictures of his microinverter array, which was a ground mount. And microinverters and ground mounting go pretty well, because it's very easy to swap them out. And he said, I know it's the most expensive system, but I could do it. And if I add these other systems that are more DC oriented, I don't know if I would have had as much success. So going from, say, the string inverters to the AC microinverters, looking at the cost difference between the two, for most customers, it's going to translate to 1-year payback. If you have higher electricity rates than average, then the price difference may not be as substantial. But like, say, here in Mississippi, where the price of electricity is low and solar is already at a 12-year payback, if I can take that 12-year payback and reduce it to an 11-year payback, the number of successful project conversions I have is going to go up by a incremental percentage. So if you're cost conscious, the AC microinverter system may not be the best way to go. All right, so when you've picked out your inverter, whether or not you're going with a string inverter, microinverter, or DC optimizer system, let's go over some terminology. We got our solar cell, and then the industry will refer to what you think of as a solar panel. It refers to it as a solar module. And the reason is that the term panel already has other meanings. It could be an electric service panel. You could be an energy distribution panel that the solar array is tied into. That could be a solar panel. I could have a solar monitoring display, and that display I could call that's my monitoring panel, or that's my solar panel. So if you want to be technical and maybe solar nerdy, referring to the solar panel itself as a solar module is a little bit more clear, whereas the panel technically would be a grouping of modules. So, a solar module is a solar panel. A solar panel isn't necessarily a solar module. The circuits on the DC side, the jargon is string. So like on the AC side, the jargon would be an AC branch circuit. On the DC side, we call them strings. And the process of determining which modules go on which circuit is called string sizing. And so how you determine how many modules go on which circuit is a function of string sizing software, which the manufacturer provides. So after you pick out your inverter system, you go to the manufacturer website and you say, okay, I'm using this particular solar module. Maybe you got some good pricing on it. And I got this particular inverter, and it's telling me, okay, if you're using this module and this inverter and you're in this temperature range, here are all the possible circuit configurations for your array. So it's not going to tell you which is the best configuration. It's going to leave that up to you. But what it's going to tell you is all the allowable configurations, so that if you went with less than 11 modules in series, your voltage would be so low that the array wouldn't turn on until 11, and we want the array turning on at 8. And so they're limiting on the low end on just what's practical for the inverter to function. On the higher end, it's more like if you went up to 15 modules in series here, you would be above that 600 volt threshold limit for National Electric Code. And then if you went to 12 modules in series, or 13 or 14, that just might be oversized. If I have 33 solar modules, that would be a 6.6 or maybe 6.7 kilowatt array. And SMA, again with that Apple mindset of let's limit the functionality but make it work more consistently, they're saying, well, we don't want you to overpower the inverter. We want something that's decently sized. And generally, you're going for a solar array that's about 20 to 30% larger than the output capacity of the inverter. And so with string inverters, you are limited to some extent. In this particular inverter, this is an older module. This is an older inverter, and it only has one PowerPoint track. So you have to do one of these configurations. You have to do one string of 11, one string of 12, one string of 13, or two strings of 11, two strings of 12, two strings of 13, or three strings of 11, and all the modules on the rooftop being plugged into these circuits, they all have to have the same amount of sunlight, which means they can't face different directions. You can't have uneven circuits, because then you'll get uneven voltage and amperage in the circuit, and that can confuse the inverter tracker. And so the string inverters also have this reputation for being very limited, because say I could do a 26 module array, or 28 module array, or 33 module array, but there's no 29 or 30 or 31 or even 32 configuration. So, what I do on my array layout, I might have to remove a few modules to get it to work. on string inverters that have multiple power point tracking. So not just one MPPT, but multiple MPPT, the strings no longer have to be uniform. You can have them facing different angles, different directions. You can have different numbers of modules on different circuits. And so the design flexibility that you get with microinverters and DC optimizers, where every module is its own system, and so you can face them whatever way you want on the same circuit, that functionality has been added to string inverters to the point where, I believe that string inverters are now good enough for solar site selection, under the mindset that, it doesn't, even though you're using a shade mitigated inverter system, it still doesn't make sense to put solar in the shade. And so when you do have shade on your array and it's a well-designed array, it's a very temporary shadow. And so we don't need module level granularity. Circuit level granularity is good enough, in my opinion. Now that's not true for all job sites. Okay, so now we're doing a DC optimizer string sizing. And so now we don't have to just select the inverter, we also have to select the optimizer that works with our particular module. And so in this design, I've used an unconventional thin film module. And so this is a 150 watt SIGS panel. Most solar panels are going to be up around 40 volts. Thin film operates at a different light spectrum. It's much higher voltage, much lower amperage. And so now we have our modules being 80 volts instead of 40 volts. That's going to require a different module level box to do your voltage correction. And so here for Half Moon's array, we've said, okay, if we wanted to use a DC optimizer system, our roof tilt is 18 degrees, our azimuth is 180 degrees due south. We fit 132 modules onto the rooftop. It tells us that that's a 20 kilowatt array, and we've inputted our solar panel. And then what it tells us is, look, here are all our different optimizers, and what you have to use is either the P405 or the OP400 EV. And you can have one per module, or you can have one for every 2 modules. And so one for every 2 modules, I actually do like that because it's cheaper. On the other hand, the problem with these DC optimizers, particularly when you're doubling them up, is you got a solar panel here, a solar panel here, and then you have, let's do 4 or 6 solar panels. So here's your 6 solar panels, and now you have a DC optimizer on every other panel. So here's our DC optimizer, our DC optimizer, our DC optimizer, and that's all going to be mounted to the rail under the panel with the clips going in between, clipping the module frames together. But the problem is the connections that come out of the optimizers plug in to each other, and then the panels would plug in together, and then the 2 whips of the panels would then plug into the box. And the problem is the connectors that go to the panel and the connectors that go to the optimizer, and then the connectors that come off of the solar panel that need to plug into each other and also plug into the optimizer, they're all the same connector. And so you can see if these are all the same connectors, instead of just doing an easy install where you're just plugging in the module into their next door neighbor and snapping and going, now for every 2 modules you install, you have to play this game of getting all these 8 connectors involved correct. And if you don't get them correct, they're still going to plug into each other. And if you make that mistake and you install the whole array and you go to commission the system and your wiring is messed up, guess what? A, you're going to fail inspection. You got to get back out there a week later. B, you have to get up, which is even worse, you have to get up on the rooftop and start taking the array apart. And so you might make a mistake and go where, well, let's do one optimizer for every 2 modules because JR said you don't need module level granularity, and this will be a little bit cheaper than 1 per module and make a little better use of our budget. But then it can cause problems with the installer, particularly if it's a new to solar installer. And so that's why I don't really recommend the DC optimizer system for brand new market entrants, is because it's the wiring and cable management of just getting all this cable up on the rooftop in a workmanlike way can be quite difficult. In fact, I've only recently kind of mastered my DC optimizer cable management. And what I do now is I assemble the whole rail and cabling system except the modules down on the ground and then hoist the rails up to the rooftop kind of pre-assembled, simply because otherwise it's just very complicated when you're up on a roof and it's hot and it's slanted to make sure that everything is up to 100%. And so here we have our final screen. It says, okay, you have a 20 kilowatt system. And while maybe a 15 or 16 kilowatt inverter would be ideal for that, they don't have a 15 or 16 kilowatt inverter. So they're saying, okay, well, you could use 3 6 kilowatt inverters, or you could use 2 10 kilowatt inverters. And we recommend 2 10 kilowatt inverters where there's 3 circuits per inverter and 2 modules per optimizer. And so just like we saw with the racking system, it'll tell you which inverter you need to use, and it'll tell you what your circuit configuration is. So now we have our modules, our inverter bill of material, our racking bill of material, and how many modules go on which circuit. And at that point, where the circuits are at, how the circuits are actually divided up on the rooftop, where they start and where they stop is kind of where the solar designer might become a little bit more of an artist than they usually are. You know, because these circuits are still by and large plugging into their next door neighbors. And so the circuits have to be contiguous. If they're not contiguous, if you want to start a circuit over here and then land it over here, you can build a jumper cable. You know, that's all right, but you know, that's buying 2 connections, building the cable, additional cable management. It's just you know, it can be you know, you want to reduce the number of jumpers. Now, you do have a choice of how many circuits you're going to use. I mean, we saw that the recommendation was 6 circuits, but we also saw that we could do 8 circuits. And so what are you going to do? Are you going to do 2 circuits of 11, or you know, 3 circuits of 10, or you know, 6 strings? You know, how are you going to divide it up? Well, I would say that my previous approach to solar design, I was going for the least total material cost. And I don't think that's absolutely the best way to do it, because sometimes cheaping out on material cost can increase your labor or even maintenance costs. So let me give you an example. This is what I would call the snakes in a basket approach, where here's circuit 1, you know, here's circuit 2, here's circuit 3, and we can just kind of see that. And maybe here I'm at the end and I have to stretch that. And the way I would do that is underneath the array, instead of landing the optimizer here, I would land it here. And that the cable whips from the module would still reach. And then the whip from the optimizer to optimizer would still reach, so I wouldn't have to build a jumper cable. So you can do a little bit of strategic placement of this stuff if you really want to. But this is the snakes in a basket approach, where you're really just trying to do the most compact string layout, you know, that you possibly can, in order to reduce the number of circuits on your rooftop. Fewer circuits means fewer breakers, less install time, less material cost. Great. But on the roof, you're plugging the modules into the manufacturer provided optimizers, or you're plugging the modules into the manufacturer provided next door neighbor. And so the connectors just snap together. But when you get to the end of the circuit, you have to build a connector and run that circuit back to the inverter. So guess where the failure is? Now, I used to say that the inverters were the #1 part of failure in a system. That's no longer my experience. My experience is that the connector that is built in the field is the #1 failure point. Because this connector is not, it's a standard format called a MC4 connector, which is a housing that has a male and a female end that's protected by a housing. And so you go and you take your single conductor cable and you crimp on a metal attachment, and then you screw on a housing for it, and they click together, and it's a MC4 is the name of the standard connector. But it's made by a variety of manufacturers, and there is a subtle quality difference between the MC4 connector that costs like 60 cents and the MC4 connector that costs $1. You know, that you have your single conductor cable, and then you have a metal connector that you're crimping onto it, and this metal connector could be U-shaped that gets crimped, or it could be a complete circle that gets crimped. And sometimes these U-shapes, especially if you're using the cheaper, $40 crimp tools that you can get off of Amazon instead of the $500 crimp tools that you would use as a listed tool on a commercial or industrial project, that crimp might not make. And then the housing connector is really bad. It has this kind of plastic screw connector that tightens it all up. And what I found is if I don't tighten that little end cap of the housing, sometimes the connection doesn't fully make. And so the problem is, even though you shouldn't have a failure with your connectors, now I don't trust anyone to make my connections because I've fixed them too much. It kind of depends on if you're using a helper or an actually certified trained electrician who knows proper workmanship. But if one of those connectors fails and it's sitting right here in the middle of the array, you got to start taking the array apart to fix it. And so alternately, instead of doing 6 circuits, it might be better to arrange your circuits where we got 1, 2, 3, 4, 5, 6, 7, 8. It might actually be better to start all of your circuits at one end and then go all the way across and actually build that jumper cable and keep going. And then start your circuit here and build a jumper cable and then keep going, and have all of your circuits kind of start and stop at the edges of the array so that those connectors are field serviceable. And then at that point, rather than running all of these home run cables all willy-nilly coming out of the array, if all of your home run cables all end up on the same section, that makes a nice clean wire run into your transition box. If all these connectors have to move onto the other side of the rooftop, you can do it in one bundle. And the problem is your circuit layouts and where the circuits start and where they stop. This kind of project documentation may actually never be developed by the installer. They may know so much about solar, and again, remember the design phase of the project has really been underserved because of the need to rush the projects to market because of subsidies, that the installer may just be doing this in the field, relying on his knowledge, and then he leaves, and then he moves, and then one of the connectors fails, and the customer gets someone else out there. They don't know what's underneath the array. The array is just, and a couple of inches up off of the roof deck, you can't see where the circuits start and stop once the array's installed. And so, obviously, project documentation can help that, but what are we going to document every single thing that we do always? Maybe you should in this particular case, but what an electrician would say is, you want to have your circuit layouts be as straightforward and logical as you can, and there's really no reason on a solar array, if you're landing your circuits at the edges, for any solar installer should be able to get up and service the array. And so I've actually kind of backed down on going for fewer circuits. And if it means that I have to install one or two more circuits to achieve a logical and straightforward circuit layout, then that is what I would recommend. I mean, it's always going to be more cost effective to fill up your circuits with as many modules as possible. But if it's a difference between doing, 5 circuits of 15 modules, or 6 circuits of, I don't know, I'm just guessing, your 12 modules or something like that, then I would go with the extra circuit, pay a little bit more in material costs, but have a much more serviceable solar array. And even some of the design software out there, the design software doesn't really generate this documentation either. This one design software called Solar Design Tool, I will mention them again, though they're the only ones that I know of that after you do your array layout, it'll actually assign each module for a circuit and then allow you to rearrange that so that you can put it into a better layout and provide a map of what modules go on which circuit. But as you can tell, this doesn't really denote where the positive end is and where the negative end is. And so you can't just rely, while solar design software does a lot of project documentation. And the danger is some of this solar design software does so much project documentation, you can literally go from your array layout to your permit document in just a few clicks. But that doesn't necessarily mean that all of the construction documentation is generated so that a mainstream electrician can just look at the plans and say, okay, I know what to do, let's do it, as they could with pretty much any other electrical device. And so, that's really where the design engineer has a big opportunity to come in and corral the solar designer. Like if you're brand new to solar, and you're in a competitive bid situation, and you're bidding up against a couple of other experienced installers, and you're the new kid on the block, you have to really hammer home why you are more professional than the existing guys in the market with all of the experience. And if you can say, look, here is my circuit layout for you, and I'm starting and stopping all of my circuits at the end and then just running my circuits straight across instead of kind of snaking them through the array, why don't you go and ask the other guys for a circuit layout? Then you get yourself out of that competitive bid situation, and you're presenting yourself as more professional. Now, you have to remember that the guys who are in solar today, they're not engineers, they're not architects. They're people who wanted a new career, and maybe they go so far back in the industry because 15 years ago, electricians did not want to do solar. And so you had to use the kind of hippie who knows about electricity running his solar business out of his garage to do your project. And that hippie who runs solar out of the garage to do the project might know everything there is about solar. They might not know how to use AutoCAD. Generating that construction documentation, they never do because they're the only guy in town. So if something goes wrong with the array, they're going to know the details and can go out and do the maintenance. But their level of generating professional installation and maintenance documents for solar is not. There's some opportunities there. So solar modules grow in efficiency every year. On the higher end, you get up into now it's more like a 22 to 23% range. On the lower end, you're in around a 17 to 18% range. So like SunPower and LG and Panasonic, they're kind of leaders in higher efficiency modules. The value range modules, your Chinese manufacturers, Canadian Solar, which ironically is also a Chinese manufacturer. They generally go in the 17 to 18% efficiency range. If I'm in a low electricity market, if my electricity costs 11, 12 cents a kilowatt hour or even less, the higher efficiency modules are so expensive that they're going to ruin your economics. I'll sell high efficiency modules to customers, but that's like if they're the luxury car dealership owner and they don't really care about the system, they just want the best. I'll give them the best. If I'm in Long Island, New York, or San Francisco, and the price of electricity is 3 times the national average, yeah, squeezing a few more watts on the roof with a higher efficiency module, even though it might cost 10 or 20% more than the other guys, or even 50% more, sometimes 100% more for the very tip of the top, not the silicon module with a glass on glass back with thin film layer applied to the top, kind of like what Tesla wants to build in one of their factories that is not yet ready. But if I want the tip of the top, that still can make economic sense in your very high-priced electricity markets, especially in an area like San Francisco or Long Island, New York, your real estate space may be quite limited. And spending a little bit more on your project to squeeze a little bit more power out of your array could make sense. But for most of the United States, you're going to want to look for modules in like the 18% efficiency range. And what this efficiency is the amount of energy that's coming from the sun and hitting the entire surface of the panel, how much of that energy is being converted into electricity coming out of the panel. So we've talked about shading, we've talked about using sun angle azimuth charts to sketch the rooftop. It's not the only way to do site analysis. Aurora Solar and their rival Helia Scope, they both use LiDAR data, which is how autonomous vehicles can see objects in the road. The same way they fly these LiDAR drones over the neighborhood, and it'll pick up topographical information. So this LiDAR data, where it's available, is quite accurate. It'll tell you things like roof slope, the height of the roof, the height of a chimney, the height of nearby trees. And it's been tested by National Renewable Energy Labs to be within 3% of the most robust on-site evaluation measures for shade analysis. Not just using a little, this is called a solar Pathfinder, and it shows you, what time of day for what months of the year nearby objects will cast a shadow exactly where you're standing. The higher end versions of this product will take digital photos of multiple points on your rooftop and then kind of sketch the horizon view or stitch the horizon view together to tell you where you can go or where you can't. You used to get up on the rooftop and do all that stuff by hand. I stopped doing that when I realized that trigonometry was just as good today as it was, 1,000 years ago. But where you do have that LiDAR data, the issue is if you're installing solar in an area that's going to get shade, it becomes complicated to give an accurate energy estimate of how much energy the array will produce. Now, what I've done in this model is I've used my LiDAR data, but as you can tell, I've grown the trees and made them larger so that we're evaluating the shadows on not just where the trees are today, but where they're going to be at in a few years down the road. Helia Scope is a software that it has fewer bells and whistles than Aurora. So Aurora, you can generate a 3D model. It'll actually change the aesthetics of the module based on what module you select. And they're doing energy analysis down to a 3-inch by 3-inch plot. And so they're actually going to be doing an energy evaluation of every single module on the rooftop and give you really good 3D images. There's ooh and ah and impress the client. But this Aurora Solar, the software costs about $350 a month, whereas their rival Helia Scope, the software costs like $100 a month. And it does shade analysis as well, and it also does a free trial. And so in our Design Your Solar Roof class, we kind of go through some of the process of clicking on your roof surfaces, sketching it out, assigning it height, and doing a shade model. But the real advantage of Helia Scope is because it's more simple than Aurora, you can do, like with Aurora, for example, Aurora is programmable. And so you can tell Aurora what module you like to use, what inverter you like to use, what array configurations you like to use in terms of rows of modules and not doing little small sections, but doing nice uniform selections. And they actually have a optimizer that will design the whole array for you with a click of the button once you get it all programmed correctly. Helia Scope is a much more simple interface where you essentially just you take the overhead picture of your rooftop and you sketch out the roof, and it fills it in with modules, and then you would give whatever you sketched out. It could be a nearby tree. You assign it some height, and it builds a 3D model, but it doesn't really show it to you. You can export it to CAD if you really wanted to. You can do that with Aurora too, but what's nice about this is when I used to do site evaluations, I would go to site, get up on the rooftop, do very detailed modeling, and then go back to my office, determine my final array layout, and then go and do my performance estimate. Now with Helia Scope, I could sketch multiple roof surfaces and then give multiple configurations and multiple proposals to the same client. And so I can say, look, if we just did the south side of your rooftop and we didn't cut down that tree, this is how much energy you'll produce. If you do cut down the tree, this is how much energy you'll produce. If we don't just do the small section on your ideal roof surface, but we cover the entire roof, that's how much energy you'll produce. If you cut down the tree, that's how much energy produced. And so you can get your client to choose which configuration they want, what kind of shade mitigation they're going to do. And that level of that discussion, having it ahead of time, definitely is a good thing. Now, probably my favorite solar design software is Solar Design Tool. And it might be my favorite because they're kind of the underdog. Not as many solar guys use them. But what I find is, sometimes you need to do shade analysis. Sometimes you don't. You usually don't need that accurate of a performance model because you're going to be conservative and undersell and over-deliver, at least at the residential level. Once you get into commercial projects and you're dealing with hundreds of thousands, if not millions of dollars of financing, then yeah, you want a more accurate performance model. But a more accurate performance model should increase the amount of energy that you're proposing. Otherwise, if you're not being accurate, you need to be conservative in what you're putting forth towards the client. What Solar Design Tool is, they say, we're not going to do shade analysis. There's other guys that are much better funded than us. The Solar Design Tool costs $50 a month instead of $100 or $350. But what Solar Design Tool does is you put in your array layout, once you've finalized your array layout, you put in your array layout, what modules you're using, what inverters you're using, all the stuff that you see in a string sizing software provided by the manufacturer. These solar design softwares have incorporated for dozens of manufacturers and dozens of products. So they're really more like one-stop shops. And what Solar Design Tool does is once you're done with your array design, it'll ask you, well, how far away is your point of interconnection? What conduit are you using? What cable are you using? And it'll go so far as to generate a National Electric Code report with all of the calculations that a permitting board is going to look at ahead of the project. And so if you don't know what you're doing in terms of generating permit applications, Solar Design Tool is not only is it good for working with, but it's also a good tutorial for what you need to know to get into solar power. And the Solar Design Tool does a free trial, no obligation free trial as well. So, that's definitely worth looking into. So just as an example, this is a one-line diagram. That's an electrical diagram. And what this is we got Half Moon's 20 kilowatt south-facing solar array on microinverters of different lengths, and then we're landing them on a sub panel, and then it's interconnected on its own point. So the load panel is over here, and the utility connection is down there. This is called a supply side connection. We'll talk about it in a little bit. But this entire document is 100% computer generated. So I didn't put in any of this information after I was done with my array layout. So I didn't, all of this gingerbread is computer generated, and it provides you a professional permit document that, particularly if you're doing solar in areas where you're brand new and the inspector doesn't know if you're doing things professionally. I just had one of these. I did a install on a new electric grid. They actually brought the head of the utility out to inspect the array, and for one reason he didn't know who I was, and he wanted to make sure that the array is being installed in a workmanlike manner. And so we're flipping through the permit document, and he says, well, do you have this and do you have that? And then he gets to a one-line diagram and he says, oh, this is great, this is more than enough. And that immediately starts you off on the right foot when you're dropping off your permit application. So what about performance estimating? The software that I recommend is PV Watts. It's a free software. Well, it's put out by the Department of Energy. It's a bare bones software in terms of it's a very easy software to use. You pretty much just put in your location, and then you put in your array size, and it'll tell you how much power it'll produce. And so what I recommend us doing is going to PV Watts and putting in a 1 kilowatt solar array and seeing how much it'll produce, because that creates a scalar. If I know that for every watt I'm producing, for every watt I'm producing 1.4 kilowatt hours a year, I can keep that number in my head. And so when my client comes to me and says, well, I use 1,200 kilowatt hours of electricity a year, in the back of my mind, I can be, okay, what's 8 times 1.4? What's 9 times 1.4? Okay, you need about a 9 kilowatt solar array to produce 1,200 kilowatt hours of electricity a year. And so if you know this scalar in the back of your head, you can really easily do paper napkin performance estimatings of system size. And so how much energy does a 5 kilowatt system produce a year? That 5 kilowatt system produces 7,000 kilowatt hours, because I know what this scalar is for my area. All right, well, what about tilt angle and orientation? Well, you can determine all this stuff and run your own experiments using PV Watts. When what PV Watts will do is it'll clue you into local weather stations. And then based off that local weather data, it'll calculate how much a solar array will produce in your local area, and it'll break it out on a month-by-month basis. You say, well, is that accurate enough? The number one mistake I think people make with PV watts is they get to this final screen where it shows you your annual performance data and they don't scroll all the way down to the bottom where you can actually extract the data on an hourly basis. You know, what that data, that raw material data does is it provides you with information like your insulation that's hitting the surface of the array. It'll provide you with ambient temperature, which I hid in this slide, but it'll convert your ambient temperature to your module temperature. And so if you want to know how hot it gets up onto a rooftop, well, PV watts will tell you that. If you're doing off-grid modeling and you want to know how many days in a row of overcast weather will you get in the wintertime, PV watts will tell you that. If you want to know hour by hour how much power your array is producing because you want to model time of day or time variable metering structures, you know, PV watts has the raw data that you can use to make those calculations. And this is the same data that all the professional softwares use to make their calculations. They just have a higher degree of granularity so they can be a little bit more accurate. You know, so I like using Kansas City, Kansas as an example because it's kind of in the dead middle of the United States and has pretty much average sunlight for the United States. And so, you know, the East Coast has less sunlight but cooler temperatures. You know, the West Coast is kind of the exception where you get into much higher productive electricity pricing and production. But, you know, it's like, well, in the East Coast, your production goes down, but your electricity pricing goes up. In the middle of the U.S., your price of electricity goes down, but your production goes up. You know, Kansas City, Kansas, about average United States. It's just under that 1 to 1.4 ratio. And so the question is, okay, if I have a 1,000 watt or 1 kilowatt array, what size of an inverter do I need? Well, you can actually use PV watts to determine that because it'll tell you the actual output on an hour by hour basis. And what I can go and see is, you know, here we are on May 12th, and my solar array, my 1,000 watt solar array is only outputting 875 watts. And actually, if I go and look at every single hour of production, PV watts is telling me that this 1 kilowatt solar array will never output more than 874 watts. And the reason for that is the wattage rating of your solar module is done at 1,000 watts per meter square of irradiance, which is really only happening when the sun is directly facing the module. It also occurs at 25 degrees Celsius. And so we can see when I'm getting 1,000 watts per meter square in the field, it's the middle of the day and my cell temperature is much hotter than 25 degrees Celsius. And that temperature effect is dragging down the performance of the module. So when you're most productive, you're still not really getting the test condition that the module was rated for. You know, the test condition of the module rating is really a day like today where it's cool, it's like 60 degrees outside, bright and sunny, no humidity, you know, the birds are singing and everyone wants to go have class outside because it's a beautiful day out. Like that is standard test condition, but it's not 60 degrees Fahrenheit most of the year. And then when it is 60 degrees Fahrenheit, that's in the spring and that's good, but very soon it'll be the winter and you're getting less sunlight. So in short, you're never going to need the output capacity of the array. If you have a 1,000 watt array, you will not need a 1,000 watt inverter because you'll never get to 1,000 watt output capacity. You know, having a 800 watt inverter on a 1,000 watt array, it's really like, okay, well, what's the difference if I went from 800 watts to 1,000 watts, given that there are some hours when I'm producing more than the output capacity? Well, first off, can I do that? Can I have the array producing more power than the output capacity of the inverter? Will that hurt the inverter? Will it hurt the solar array? No. I mean, if the solar array doesn't have an inverter attached, it's sitting up there at full power, open circuit voltage, and it's just not doing anything. It can take having some power that's unused up inside the array. If the array could produce more power than what the inverter is capable of, it's just that some of that power will remain untapped up in the array as elevated voltage. But if my inverter costs 20 cents a watt and I upgrade it by 200 watts, that's going to be a $40 upgrade. And if I go and I say, okay, well, only for 16 hours of the entire year do I get above 800 watts, just the maximum is 874. So let's just do, if I'm gaining 74 watts for 16 hours at 12 cents a kilowatt hour, it's just not going to, it's not worth it to have a full-sized inverter. And so if your installer is undersizing your inverter, that's just a very standard practice. And so here's like the temperature data where, most of the time your irradiance is not at 1,000 watts per meter squared. Most of the time it's at 800 watts per meter squared. So, when it is at 1,000 watts per meter squared, your cell temperature is generally above 25 degrees Celsius. And on your spec sheet, there are temperature coefficients, like this temperature coefficient of power, that says for every degree Celsius above standard test condition, you're going to lose 0.4%. So just from temperature alone on that 35C day, you're going to be, or 35C cell temperature, that could be a 25C day, but the cell temperature could have elevated to 35C. So on that day, I'd be losing 4% because of heat alone. And then if you're in Phoenix, Arizona, you can use PV watts to determine how hot your rooftop will get, and your cell temperature in Phoenix can climb all the way to 71C. On a 98 degree day, your solar array can get up to 160 degrees Fahrenheit. So at a 71 minus 25, you're looking at a 46 degrees C temperature difference. You're losing about 20% of your power output in Phoenix, Arizona in the summertime due to heat alone. So PV Watts is a very versatile software, and while we don't have too much time, right before we go on break, why don't we just pull open PV Watts? I'll put the link in the chat, and so if you can play around with it after or during the break if you want to, and go into all audience send. If I'm using PV Watts, let's go ahead and do Philadelphia, Pennsylvania. Eagles, Super Bowl winners. Now I like doing a 1 kilowatt array just for modeling because it develops that scalar. Module type, the standard. I'm going to go and put it on a roof, although you can do tracking arrays. System losses, it does 2% for soiling, which is on the high end, I'd say. Like, it is good to wash your modules, but I wouldn't, a ground mount is going to need to be washed more. An array near a dusty road or a dirt road is going to need to be washed more. But generally, for washing your array, you'll want to do it about once every 5 years. You want to take a damp rag to the array and get all the dust off. If you're not in a particularly dusty environment. So 2% soiling is on the high end. 3% shading, that's more to account for morning and evening shadows stretching across the landscape and maybe the inverter not turning on until even if it's unshaded, there's still a little bit of sunlight in the morning that occurs before the voltage of the module elevates to turn the array on. So I'd call that shading too. They're not modeling snow. Fortunately, wintertime isn't your most productive season. So when you have snow sitting on top of your array for the entire month of December, you're losing more like 6% of your production instead of 8%. So having snow sit on top of your array for 2 weeks in the wintertime is only going to impact your performance by about 3%. Module mismatch is not really a thing anymore. Or rather nameplate rating. It used to be that the modules had a plus or minus tolerance in terms of their power output. Now it's more like a plus tolerance with a bare minimum. Now, mismatch acknowledges that some modules are going to be more productive than the others, and the weaker modules, just slight variations in the silicon cell, are going to drag down the others. And if you're using optimizers or microinverters, you could just get rid of that entirely because every module is its own system. And so just being very conservative with your performance estimating, either I usually will model PV watts at around 11% loss factor, but that's because I have arrays in the field that I can compare it against. Voltage drop is around 2%. Code, I think, is at 3% now, but if you're in solar, you're usually trying to design closer to like a 1.5% voltage drop. And of course, PV watts is going to take that off the top. But voltage drop in solar, the voltage drop for the module that's furthest away is going to be 1.5%. The module that's closer might only be 0.5%. So that's where, again, where commercial software provides a little bit more aggressive modeling. This is conservative modeling. We have our light-induced degradation that we talked about yesterday, and this 3% system availability, that's the real area where PV watts is being overly conservative. PV watts is assuming that your solar array is going to be offline for 3% of the year. Now, that could be snow. Okay, well, Texas doesn't get snow. That could be maintenance where you've turned the array off and you're doing some maintenance work. But if your solar array is off for a week out of the year, every single year, you probably picked the wrong solar installer. But anyway, we go into Philadelphia, and then right after this, we'll take a break. But we go into Philadelphia, we pick out our 1 kilowatt array on the roof with a system loss factor. Let's just keep it at 14% and be conservative. If it were, we can get our roof tilt angles, like a 512 roof is 22, 612 would be 26. Let's go ahead and say Philly's going to be on a 612 roof pitch. And we'll do a 26-degree tilt angle. And then we click go, and what we see is the our system production. The most important thing to keep in mind with PV watts is that here in our map, let's get it to load up. There we go. It doesn't really. So we have all our weather stations that we can choose from. If I'm doing a solar array in New Jersey in the middle of the boonies, the question is, well, which weather station do I select? And what I would say is you want to select the weather station at, even if it's not necessarily the closest weather station, you want to pick the weather station that most fits your geography. So if you're right on the coastline here, I'm not going to go to this weather station that's further inland. I'm going to go up to this weather station that's right on the coastline in order to get my weather patterns to be more consistent. And so that's PV watts. And so our design algorithm is to measure the rooftop, select the module inverter, do your array layout, do a PV watts energy estimate, use stringing sizing software to do your final wiring configuration, develop your racking material by doing a racking balance of system configurator, maybe use a solar design tool to generate permit documentation. And at that point, you would pass it off for any structural or electrical sign off and procurement. Now, one thing we have to remember is it's not just about how much electricity you produce, it's also how much that electricity is worth. I mean, the solar production between California and New York City might vary by 50%. And so, I see on the news, it's like, oh, well, solar may work for Albuquerque, New Mexico, but it doesn't work for New York City. Well, that's only half of the equation. The other half is the price of electricity. The price of electricity in New Mexico is about 9 cents a kilowatt hour, whereas in New York City, it's upwards of 22 cents a kilowatt hour. And so the price of electricity varies across the country much more greatly than the amount of solar production. And so actually, the price of electricity is what's the driver of the solar industry, not necessarily how much sunlight you get. Even in a state like Alaska, where you don't get hardly any solar production, you still see solar because the price of electricity is so expensive. So even though your production in Alaska is way down, you'll still see solar there because their electricity price is way up. The price of electricity is as important, and because it's more volatile than solar production, we see robust solar markets on the northeast coast, whereas in the southeast part of the United States, you get lower production and lower electricity pricing, and so it's much more of a challenge to do solar projects in some sunnier climates, and more economic to do solar in some cloudier climates. If you want to know how much solar will produce on an overcast or cloudy day, you can model that in PV watts. It'll tell you the difference between ambient or diffuse lighting conditions. And solar produces about 1/3 of what it will do on a cloudy day versus a sunny day. Looking at some project budgets, we got solar modules. Now that the import tariff for solar has been passed, I don't know if the aluminum frame on that solar, which is already subject to 2 levels of import tariffs, if the aluminum import tariff will cause module pricing to go up even more, or if it'll already be considered included in that aluminum import tariff. But right now, good module prices, if you can buy them in the 60 to 65 cent a watt range, that's about where your quality value range modules will be priced in. Same modules in Mexico would cost 40 cents. If you absolutely are in a situation where solar's too expensive but you need it, if it's your own little hobby project, if you want to build a little cabin in your backyard or a garage apartment, or you want to add power to your barn, going with a less professional module, a scratch and dent sale, a module that's a few years out of date, just stuck in some inventory somewhere, it is possible to get better deals on modules than 64 to 65 cents, but they're not necessarily something you'd want to put in front of a client. Inverters can be as cheap as 15 cents a watt. That would be like for a single MPPT tracking string inverter. Usually the inverter systems that I'm using are up in the 30 cent a watt range, regardless of if they're the DC optimizer system or a higher end string inverter with multiple power point tracking. Racking costs, I'd say I'm actually a little bit out behind the trend on this. The racking costs I've seen out of the projects I'm currently doing are more in this 12 to 15 cent range. So that's racking costs have come down. When I contract out the project and I hire electricians and I go out to the field and I make them do all the work, but I'm telling them what to do. So kind of like a construction manager managing a subcontractor. I find that my electrician installation budget is running around 30 to 35 cents per watt, and that's kind of just for the labor of the electricians. If you go to a turnkey solar installer, they're going to want to make some additional markup on that. Engineering costs, blame the permit process, but a lot of solar does not require a structural stamp. I will often recommend it as an add-on, or if it's my project and it's a metal rooftop, that's when I go and get a stamp to make sure I'm in line. There are online structural engineering services that specialize in rooftop solar where the cost of a stamp, if you're referring business in bulk to these engineering companies, can get under $500 for a basic residential straightforward stamp. So it's not like the cost of an engineering stamp is a huge issue in your project, and it is one way that you can appear more professional. Then you got the profit, overhead, permitting, and supply chain costs. I'm doing right now. I'm doing solar as a subcontractor, where a company in California is doing the sales, most of the design work, and so they're paying a sales rep a commission. They also have an online project manager. When you get more people involved in the project, you will have more costs. When you get into solar financing, there's the due diligence for your inspection work goes up a little bit. You need to make sure you're taking good site photos and documenting the install. And then some states do a sales tax exemption, others don't. And so what we see is that according to like National Renewable Energy Labs, according to budgets that you could get from a turnkey installer who's hungry for work, we see that solar could be in the 250 a watt range. Right now, if you go out and go out and just get one bid from one solar installer, he's probably going to give you a quote in the 330 to 350 a watt range, and that's basically more of a specialty margin. And so it is very good to go out and get multiple bids. I mean, you will see a substantial drop in price if the contractor knows that you are in a competitive bid situation. Let's see, and this really should have been when we're talking about module efficiency. We already covered this point, so I'm going to keep going. What this study says is most solar owners want less than a 10-year payback, and so in a state like Mississippi, I have to go to the very low end in order to sell solar projects that are for economic reasons, not for battery backup generator alternatives. So why don't we take, the way that we do our payback is you take the total install price, factor out the impact of the tax credit. The 30% federal tax credit for solar still exists. If you're expanding your array or adding a battery to the array, the tax credit is still applicable. So if you already own solar, you want to start thinking about adding batteries before the tax credit steps down in, I think, 2021. Divided by how much energy you produce, I like to keep all my stuff in dollars per watt. And so if I'm at like if I'm at a 260 a watt, and then I have a tax credit, now I have that 1.4 kilowatt hours per watt per year, and I'm at average electricity pricing for the US, That's that at 260 a watt, average production, average electricity, we're at about a 12-year simple payback for solar for most of the country. So most of the country, the solar market still really hasn't emerged yet because we're in this 12-year payback range. On the other hand, unsubsidized solar really can't get to a 3 or 4 or 5-year payback, because if it did, everyone would be running out and buying it, and installers would keep their price to the point where we're a little bit there, they can make a little bit more money. So it's still definitely an industry where you have to watch your costs and make very hard cost-based decisions, and whether that comes out of labor or material, it has to come out of somewhere for the industry to be mainstream. Now, one big point of contention today is how you are reimbursed by the utility for the electricity that you export onto the grid. A utility may take the position that, hey, it's not our business to buy electricity from our customers. We're in the business of selling electricity to our customers. It may take a state law, like a consumer protection law, to say that no, you have to be compensated for what you export. There's actually a federal law that requires the utility to purchase the energy at avoided cost, which is about 20% the retail price of electricity. So the federal buyback rate is rather small, and that would be where there's like no net metering. The electricity is purchased at avoided cost. Now, your state may have what's called a net metering policy that basically says the compensation for this outflow solar might be larger than avoided cost. Often net metering is set at a retail price reimbursement rate, and that's controversial. It used to not be controversial. I mean, back in the day, and when solar was more theoretical, you'd have discussions about, well, maybe solar electricity, because it's during peak times and it's emissionless and it's distributed, maybe that offers value that is above retail price to society. But society's not the power company. And where it gets really frustrating is when the power company is a monopoly, and so de facto the power company is society, because society doesn't have a choice in the matter. And in some of those regulated utilities, there are many regions in the US where they don't buy anything of your solar electricity for anything more than avoided cost. Actually, in the Tennessee Valley Authority region, there's only 35 residential solar arrays, because to get the avoided cost compensation, you still have to jump through a bunch of red tape, and it's you have to fight for pennies, and that sets the solar back, and that's a bad policy. Because if the utility is purchasing at avoided cost, it's cleaning the grid and lowering the price of electricity for non-participants. So in the interest of low-cost, clean energy, we shouldn't have utilities that have monopolies obstructing that process. Utilities who don't offer fair consumer policy to solar on regulated grids will run the risk of deregulation down the road. Now, you could get a month-to-month net metering policy, or an annual net metering policy, or an unlimited net metering policy. With unlimited, anything that you produce is credited to you at retail and then rolled over into your next bill. Annually, any surplus credits you have at the end of the year are cashed out at an avoided cost. If you have month-to-month net metering, any surplus credits at the end of the month are cashed out at avoided cost. If you don't have any net metering, the instant that you export onto the grid, they purchase that electricity at avoided cost. So, I think that net metering is eventually going to go away. Utilities don't want it. citizens don't participate in their public utility commission meetings, and so most states do not have consumer friendly buyback rates. On the other hand, your grid operators do have a very important job of maintaining the grid, and so maybe retail compensation is a little too much. And so there's a new term called a value of solar tariff, and that might be above retail price or below retail price. But it's kind of replacing these net metering policies to say, hey, maybe the consumer should not get retail price for exporting power onto the grid, but maybe the compensation should be more than avoided cost. So these are just some terms. Generally speaking, you should have a net metering policy if you want to do solar. If you don't have a net metering policy, you want to do small solar, so you're not exporting as much to the grid. And some of what we're working on internally is hardware to retune some of your loads that operate 24/7, but maybe we turn them off right before sunrise so that you use more of your solar electricity in your refrigeration than off. Maybe if you're doing a solar design with new construction and you're using split HVAC units, maybe some of your HVAC units are gonna variable speed loads. Maybe you want to crank them in the middle of the day and have some thermal mass inside your building to so that you can ride out the evening when you don't have that electricity on site. In general, net metering is under attack. This is what frustrates me the most about the solar industries. We've had all this discussion about the tax credit, and it took a bipartisan effort that expanded fossil fuel expansion as well as solar expansion in order to get that tax credit extended. And then you slap an import tariff on solar and it gets rid of the effect of the tax credit. I mean, in Mexico, they don't have the tax credit, they don't have the import tariffs, and solar is cheaper. So maybe all the lobbying effort to extend that tax credit, it would have been better served to say what we don't need is subsidies, what we need is better policy. But instead, what we have is subsidies and bad policy. In fact, the net metering, which really has been a right for most consumers since the 90s, the analog meter has net metering built into it because it'll just spin forwards or spin backwards. Well, now the digital meters track outflow versus inflow separately. And so we basically, the power company charged the customer to swap out a digital meter that gives them less rights than their previous meter. And in fact, not all the digital meters are set up for solar. And so, you do solar and then you have to buy a new digital meter all over again. And in the meantime, many states across the country are reducing or phasing out their net metering. Not all states, but most states, if they have net metering, it's on the chopping block. And so, for that, we have to say, okay, well, what does solar design look like without net metering? How do we make solar more cost effective? Well, for one, we need to bring the real value of solar to market. Right now, daytime electricity costs more than nighttime electricity. And so you can get a rate structure where you have a higher rate during the day and a lower rate at night. If this sort of rate structure were mandatory across every ratepayer, well, then you wouldn't need subsidies to get solar to market because everyone would go out and try and avoid that higher rate during the day, and the compensation of inflow versus outflow wouldn't really matter either. So the solar industry, in my perspective, they should be advocating for better billing structures that do not discriminate against solar, but more accurately reflect the real-time value of electricity. Then again, there's also how much does a consumer understand about electricity? So how complicated can a rate structure really be for our uneducated consumer? And that's why that's why these rate structures have not been mandatory in the past. So time of day metering can increase your solar value. It's often an optional rate structure provided by your utility. There's also demand rate structures, which in our battery class, we talk about how in the past, demand rate structures have been terrible for solar, but now when you add a battery, they can often result in paybacks that are faster than solar, particularly at the commercial level where it's not the volume under the curve that's being billed, but instead maybe 2/3 of the bill is the maximum peak. And so a solar battery does a really good job because a solar array will produce most of your energy during peak times, and then the battery can come and take over, the tail end so that you can cut your building demand rather substantially. And if that's 2/3 of your bill, you've just reduced your bill by 33% with a small solar array that only does a fraction of your energy. Whereas if you don't have net metering and you're producing an array that does all of your energy, well, a lot of that's going to be outflow in the middle of the day. And if that's compensated at avoided cost, you're not going to get good value out of it. So, the one frustrating thing about solar is that the value of solar is higher than retail if it's designed with all of its total functionality. It's just that the billing structures are not in place to uncap that value. If I was just talking with the purchasing agent of one of the largest purchasing electric cooperatives in the country. And we were talking about how solar in Mississippi is lagging behind. And I said, if we had mandatory demand charges throughout the entire region where every customer was billed just the same way that commercial customers are for their electricity, we would have a boom in solar in this state without any subsidies. But from his perspective, like him and the other utility electricians kind of shuddered when I suggested mandatory demand charges because they view that as so publicly controversial. But the comment was, well, that would be a fair way to share grid charges amongst all rate structures, whereas what's more common today is the utility will create a solar discriminatory rate structure that is just for solar users, and by and large, these solar discriminatory rate structures, where they do exist, magically reduce the value of solar. We don't have energy efficiency discriminatory rate structures, but some utilities have a phone book worth of rate structures, and other utilities just have one that everyone gets. But one thing that time of day metering, there's also time of day consumption. At what time of day does your home consume electricity? Because if I know my average consumption throughout the day and I don't have net metering, what I might do is just design a solar array to get up to that peak or something that's just larger than that peak. But I'm not going to do a solar array that could do like 100% of my bill, because all of this volume would be outflow, which would be purchased at avoided cost in my region. Then again, I am in a hot region, and a lot of this in orange, this is electric heat. And so if I'm in a hot region, I'm cranking my AC all day long. It might be that I can just add a little bit of thermal mass to my house and run the AC more in the middle of the day and kind of coast into the evening. And so for some sites, if you have this level of granularity, if you know what your load profile is, you can do a more accurate and perhaps more cost-effective design. Now, this is Aurora Solar. What Aurora Solar does is kind of neat. They take your month by month by month electric bill, and then you fill out a survey of what electrical devices are in your home, and based on your region, and if you have gas heat versus electric heat, or electric water heating versus gas water heating or whatever, they'll adjust and give you an estimated load profile to see what you're generally going to do based off your usage and typicals to your region. But that's not, that doesn't necessarily mean that it's exactly what your home is going to do. Now, this is an interesting concept here. You know, the idea is, can you put a solar array and have it face north? You know, when I was brought into the solar industry, I was told that if you put a solar array and you faced it north, it wouldn't work, because I was told that solar needs direct sunlight to work. Well, in the summertime, the sun is more up than south. So the north side of the roof in the summertime gets as much sun as the south side of the rooftop in the summer, not in the winter. But we go back to our PV watts calculator, and let's go and model a little 1 kilowatt solar array, and we're going to face it, put it on the rooftop. And remember, at roof, you're not on a rooftop, you may not be at a severe tilt angle. Let's do a 412 roof. That's at an 18-degree tilt angle. And I face it due south. Well, in my region, I'm going to produce 1,368 kilowatt hours a year. If I go and I point that module east or west, I'm going to produce 1,222 kilowatt hours a year. So that's certainly, it's less, but it's only about 120 kilowatt hours. It's only about a 10% difference between facing the module east or west versus south. If I was on a steeper roof tilt, it might be a 15% difference between an east or west facing array versus a south facing array. I could even do something crazy. I could make my array face north. You know, if I'm at a 1 degree azimuth on a 412 roof, well, look, I'm still producing power. Now, I'm producing about 300 kilowatt hours, a little less than that difference. So I'm producing, in this case, I'm producing about 25% less for a north-facing array versus a south-facing array. But guess what? In the summertime, my electricity is 20% more expensive than it is in the wintertime. So even though I'm producing less electricity, 25% less electricity, the difference in cost effectiveness might be more like 15%. And then if I'm in an area where they're only giving me avoided cost for my outflow, maybe I'm consuming so much of this electricity on site in the summertime that the north-facing array, based on my electric policy, may be just as cost-effective as a southeast or a southwest facing solar array. So it's good to check, do a complete economic model, and you might surprise yourself that what you would feel is a disqualified roof surface because it faces northeast might actually be as cost-effective as the south-facing surface. Usually that won't be the case, but there's another factor to consider in that equation, which is economies of scale. If I have some roof obstructions that I want to avoid, and so I have this apartment complex, and I can either do a 4 kilowatt array that faces southeast, or I can do a 13 kilowatt array that faces southeast and northwest. Now, the pricing example is a little extreme, but what I wanted to show is that, doing a small solar array, well, the installer is going to mark that up because he's going to want to make, there's margin, but then there's also a minimum dollar amount that he wants to make on his project. And so smaller projects do cost more than larger projects. It's not just a matter of making a minimum amount of money. I mean, it's, for this project, it's still one design. You're receiving material. It still takes time to do that. You're still mobilizing the site. It takes time to do that. And furthermore, once you're up on a rooftop and you've installed, 10 solar panels, adding another 10 panels right next to that, and adding another 10 panels right next to that, that's not doubling or tripling the time you're spending on site. What really doubles or triples the time you're spending on site is when you have multiple subarray sections to install versus one uniform section. And so actually, doing 3 small subarrays at 450 watt, that might be what you get for pricing. Whereas if you just went with something larger, you could get economies of scale discounting. And so even though this total array effectively produces less energy than the smaller array per watt, because it generates at a higher summertime rate, because you get the economies of scale, it could very well be that that array that covers the whole roof is more cost effective than the array that only covers one small section. On the other hand, when that you go with curb appeal, that new home buyer, they don't know, they see a small solar array, they don't know what the impact is on the electric bill. They just think that that's a green home. That's a home with low electric bills. That's a home I want to buy. That curb appeal or chic value of owning solar, that is large for a small array. That value gets kind of diluted the larger your array goes, to the point where the value of the array becomes much more close to the appraised value of the cash flow that it produces. In other words, small solar, the economics are a little strange because the value is not just the value of the electricity, whereas large solar, the value is much more pegged to the cash flow of the array. I'm a fan of small solar in Mississippi. For one, even when I do a large solar project, the payback is not impressive, but the project costs $20,000 instead of $8,000. So there's a lot fewer people who can buy it. For another, a small solar array with a battery would operate as a peaker plant, which is really good for demand management. So if I have a demand rate structure, a small solar array with a battery can actually be pretty cost effective. And so when I'm in Mississippi and I'm looking at solar not being particularly cost effective, in order for me to sell projects, what I would do instead is sell small solar so that people can afford it, but have the arrays be more suitable for backup power, add in more cost, do less solar, add in some batteries, and really pitch the product more as a backup generator that also produces a marginal income stream. Whereas when I'm selling a larger solar project, it's more about the dollar and cents brass tacks. So in general, south facing is the best for your overall production, although west and east are better for evening and morning. If you want to go off grid, east and west array is better than a south array because you get that full day of production. Doing south versus east and west might produce a larger array, better economies of scale, and then kind of the last surface you fill up if you have budget left over is north. But I would say the great solar surfaces are any southward facing array. West facing is also very good because generally those time of day structures extend into the evening hours. So south and west is great. East is also good if you want to go off grid, and then depending on your rate structure and roof layout and economies of scale, yes, it can make sense to have solar on the north side. Now, in fact, coming back to our PV watts calculator, now let's take the same solar array and we're going to angle it down the side of the building. So it's now at a 90 degree, it's south facing, but it's at a 90 degree tilt angle. And look, it doesn't produce much electricity, but it still produces, 847 over 1,348, that's 500 kilowatt hours. I mean, we're still producing, maybe 40% less electricity, but it's not 70% less, it's not 80% less. And so actually, if you're doing, say, an off-grid design, you might be just as worried about having, if you're all electric and you're off-grid, you may be just as concerned about having that electricity in the wintertime as you would in the summertime, because you need heat. And so putting that solar module at 90 degrees down the side of the building, even though it's less productive, it's going to not have snow on it. And so if I'm building a cabin that's off grid in northern Vermont, maybe even building the walls of the cabin out of solar panels is not a terrible idea. Like like a butt glass wall that's non-structural. There's like no solar installers out there are actually using the solar panel as a building material, but you have to remember it is an outdoor rated product for weatherproofing and the like. So that's kind of there's all the market is focused on filling up low-hanging fruit roof surfaces with solar, but there is a lot more creativity in this market that has yet to be tapped into. Also, that avoided cost electricity rate goes up in the summertime and down in the wintertime. One item that even makes net metering policies a little weaker and also makes the avoided cost a little weaker, and sometimes I have to go back and challenge the utilities on this. The Tennessee Valley Authority has their solar program is if you want retail value for the array. It's less than retail value now. So if you want something close to retail value for your solar array, you actually have to plug it into the grid and sell all of the electricity to the TVA. You don't connect it to your home. They put a standalone service on a small solar array. It's actually a costly policy, and it strips the backup power capability of the array because it's not connected to your service panel anymore. It's not a good policy. And the alternate is to interconnect the array on your load side and get avoided cost instead of retail for your outflow. And so we're actually it's problematic because customers have been participating in the near retail program, but as the value of the program has come down, the participation is now non-existent, but they don't have the paperwork in place for the load side connections. And so that's what we're kind of working on right now with a few customers. And the utility has come back to me and said, why do you even want to do this? We have the program where they get 9 cents instead of 3 cents for their outflow. So isn't it much more economic for the customer to receive 9 cents instead of 3 cents? And I say, look, guys, I want this to be for backup power. They might want to add batteries in the future, and I can't do that through your program. And I say, okay, but it's still going to be more valuable. And I say, well, hold on. When I'm selling my electricity to the grid, they're asking me for a W-9. They're reporting it as income they've paid out to me. Technically, I should report that as income on my taxes. Now, that's up to your CPA. The general thought is that as long as that utility revenue is less than what you're paying in electricity, then you're really not in business of selling electricity. You're just trying to reduce your bill. But technically it is income. You're selling your electricity. So if I'm paying income tax on that 9 cent purchase, that's going to reduce the cost effectiveness of the array. Whereas if my electricity is just rolling off retail of my bill, that's post-tax income. If I'm reducing on site at 11 cents and then selling back at 4 cents, I'm being taxed at the 4 cent sell, but not the 11 cent sell. If I sell all of my electricity at 9 cents, I'm going to be taxed at 9 cents and for all of my electricity. And so, actually when you complete the analysis, doing a avoided cost buyback, but being able to reduce your retail price electricity is often more cost effective than a power purchase agreement with the utility that's set at still less than retail. Now, the danger in all that, if none of that made sense, the one thing you need to remember is that commercial economics are different than residential economics. Residential, you're not in the business of selling electricity. You're reducing your electric bill. You're not paying tax on the cost savings that the array produces. But if you're selling your electricity, you would pay tax on that. If you're a commercial customer and you're not outflowing onto the grid, well, you're still reducing your electric bill, which is a tax deduction. And so if you're reducing your electric bill and you're losing out on that tax deduction, you're effectively paying tax on the cost savings that the array produces. Now, that is offset by the fact that you get to depreciate your asset at the commercial level, which you don't do at the residential level. You're not a business at the residential level. You're a business that's commercial property at the commercial level. So the income tax effect of the cost savings is pretty much dollar for dollar offset by the depreciation. And because it's accelerated depreciation, you actually get a very slight financial advantage. But the problem is your non-financially savvy solar installer who's been in the residential market, they go and do a commercial evaluation and they say, okay, well, you get the tax credit and you get the payback and you also get depreciation. So that's an additional 30% that you're going to get back on your taxes, and that's going to produce a much better payback than residential. If you're ever in that situation, that is not true. If you're using a residential installer and they're not on a commercial project, don't trust their income stream, because whenever you're modeling depreciation, you also have to model the tax effect that you're paying on the cost savings of the array. So that's more of a commercial issue. Now, if I'm in a situation where the utility is saying I need a W-9 because I'm buying electricity from you, at that point, it is worth it to argue to the accountant that you should pay tax on the avoided cost, but also you should be able to claim your solar array as depreciable property since you're now in the business of selling electricity to your utility. So there's definitely some good rules for CPAs and accountants to get their hands on your cash flow and make sure it's being treated properly. One problem with solar is that historically you have not been able to factor it into your home mortgage. Now, most mortgages are 20 or 30 years. The average payback in the United States for solar done at mainstream installation prices would be around 12 or 13 years. What happens when you put a 12 or a 13-year payback into a 20 or 30-year low interest financing structure? Well, you're going to take more money off of your electric bill than what you'll add to your mortgage payment. And so, solar, even without subsidies or net metering or any of that rigmarole, it would explode if we could put solar into the mortgage. But that's a little chicken and an egg situation, because the real estate appraiser needs solar arrays on the roof to come to market and sell before they can appraise the array. And the array needs to be appraised to go into the mortgage value. And so they can't do that if there's no solar market in your community. And so there is a reason to subsidize solar for a very short period of time, just to get the early adopters to market so that the financial community can warm up to the market and figure out how to appraise it. And finally, this appraisal data is being rolled out. And so it's more likely to be available in solar aggressive markets like California or the Northeast coast. And if you're in a solar market that's behind the times, which is about 40 out of 50 states are way behind, and it's like California and Massachusetts and New Jersey that are bringing up the national average, and they pretty heavily subsidize solar too. But what this appraisal data is showing is that smaller solar arrays are going to be appraising, and this is at California electricity pricing. So I would take this with a grain of salt. What I would do is I'd pretty much cut most of these values in half for average markets. But even if that's true, we're going to see smaller solar appraising for around its installation price. You know, if I get out in California, if I get a 2 kilowatt solar array that costs me $5 a watt, you know, and I'm selling my house in 2 years, I'm going to get all that money back when it comes time to sell my house. If I go into a 10 kilowatt array, it may only add about $2 a watt average to my property value. And so it's actually, you know, solar, if you're doing a small solar project, if you only have budget for a small solar project, and you say, man, I wish I could take advantage of economies of scale, or man, do I really want to spend $8,000 to only save, you know, $500 a year off my electric bill? You know, one value that is not, you know, monetized in a simple payback equation is the asset value that the solar array will add to the home. Now, at a commercial level, the asset value is taken off the balance sheet through depreciation, so it's not really factored in. But at the residential level, you know, if you view solar like a granite countertop, you know, what can I do to make my home more attractive to sell? You know, putting a few $1,000s into a small solar project, you're going to retain that in your real estate value, and you'll get some incremental cash flow out of the asset as well. Now, as the arrays get larger, that value appraises for much more close in line to what the actual value of the cash flow would appraise for, much like you would do with commercial financing. One of the more important aspects of a site evaluation is to get into an attic and inspect the truss of the rooftop to make sure you don't run into any unknown issues. Now, you know, a client with a cell phone camera can usually get into their attic and take pictures to tell you what you need. Construction documentation can be useful for that too. This is a half moon roof. What we can see is that it's a very thin gauge steel with purlins above rafters, and the construction documents say they're 2 foot on center, and that looks pretty regular. And these look like 2x4s and 1x4s. You know, you want to have the truss of the roof that you're anchoring the array to, you want to anchor that to your building wall. So putting hurricane clips between the truss and the building wall is a good idea. You know, if you're concerned about lag screwing into the rafter, you can sister or daughter, you know, blocks of wood next to the rafter. You know, it's not commonly done, but you may find, you know, on the right rooftop, if it's an old rooftop and the client is adamant that they want to do the solar array without replacing the roof, you know, maybe you know, giving yourself reducing the chances that you're going to miss the rafter by, you know, only in that one section where you're running the rail across, going in and giving yourself a little bit more space to lag screw into, could provide a benefit. You know, when you put a lag screw into a 2x4, you know, that metal is stronger than the wood. It's not, if you're on center, if you're not like nicking the edge, you're going to get good pull strength and you're not going to weaken the rafter. What happens is when you remove the lag screw, like let's say you're replacing the roof, you're replacing the solar array, and you remove that lag screw, it's going to leave behind a hole that's pretty sizable. I mean, these lag screws are like 3/8 or like 1/4 of an inch thick, and that hole can weaken the rafter, so you have to fill it in with structural glue. But this is a online engineering firm, and they're, you know, in your site evaluations, they're really just looking for what the shape of the truss is, where the mounting is going to be, making sure that it's 2 foot on center. You know, for Half Moon's building, we're going into 1x4 purlins. It's a metal roof, so I went to a company that specializes in metal roof attachments, and they actually gave me pull strength for their attachments. And I thought this was fascinating because they give you pull strings for wood purlins. Okay, this is us. We're going into our purlin. We're actually going to use 3 fasteners instead of 2. Why not? As the attachment had 3 holes in it, so we're going to use them. After a safety factor of 3 is applied, the pull strength on that attachment for a pine rafter is between 400 and 600 pounds. So that's that's pretty strong. That's not going to pull out of your roof, especially when you consider the safety factor applied. This is what I think is fascinating. What about if you just attach to the decking and not the rafter? What if your rafters are irregularly shaped such that it's really impossible to design a rafter-based system? What if based on you have a weird, funky rafter purlin roof, and where the purlins aren't particularly well suited for your solar attachments, and you just had decking? Could you use the decking? Yes. Even OSB has the pull strength needed. Now look at this. Most solar installers will tell you you can't do the decking. You have to use the rafters. But our engineering data is telling us safety factor of 3, pull strength of 177 pounds. Okay, well, what's our pull strength on our attachment point? That's when we go all the way back to our racking data. There we go. Where we've gotten our uplift force. And what we can see is if we're in zone 1, the interior of the rooftop, our uplift force is 100 pounds. Whereas if we were on the edge of the roof, our uplift force was 335 pounds. So going back to our slide here with our force data on it, actually having an uplift force of 177 pounds, as long as we stick to the interior surface of the rooftop, decking-based racking systems do in fact work. And so you can find some kind of alternate racking systems that are weird that solar installers might be afraid of, that might be a better fit for your building. And that's when you as an engineer, are going to be the one leading that racking selection. So here's a racking system that is a rail-less racking system. And so on this rail-less racking system, the attachment is actually the modules laid flat directly on the attachment, and the clamp goes directly into the attachment. And while it's still being debated on whether or not that's good for a shingle rooftop, and the reason may not be what you think. For on a shingle rooftop, over time, particularly on an older roof, the surface board can begin to sag. And the real problem with that is that it's uneven. And so if the rail with your L feet gives you the ability to kind of lower and raise and lower and level the rail. And it's very important that your rail remain nice and square and level so that when you're putting the rigid rectangular modules on top of it, they remain in line and they remain square. And it's a very difficult job. I mean, you can do everything you want to square an array. It's difficult to plumb because you're on a slanted surface. Eventually, just eyeballing it is a common method, or running string across the array. But even a string is going to sag over a long distance. And if your racking is not square, your modules can start traveling up or traveling down or torquing out of alignment as you go across. So, on shingle base, the railless racking system doesn't work very well, but on a standing seam metal rooftop, where the standing seam metal rooftop isn't necessarily rated for the pull strength, You know, so it's like I have this clip that clips onto the standing seam, and that clip is so strong it's not going to come off. The danger becomes, well, we're going to rip the panels off. Well, to reduce the force on that metal panel, you got to shed weight. And so by lowering the modules right on top of that standing seam, you're going to reduce your wind load, and you're also going to reduce your weight of your array. And so that's much better structurally for the array on a standing seam metal roof to, in fact, use a railless racking system. You know, I think that that's a much better alternate than other kinds of roofs. Now, you know, again, there's products for whatever kind of rooftop you have. You know, this is actually my favorite metal roofing bracket, which is for corrugated metal rooftops. I mean, this is a butyl tape mastic. You know, it's a strong connection with 3 fasteners. You don't have to worry about the metal panel pulling out. You don't have to worry about if you need to go in and reinforce the rooftop underneath. You know, that's just the problem with your standing seam metal rooftop systems is if you use a clip and then you use a rail and then that span goes 4 feet or 6 feet, you know, the panel itself may only be a foot and a half wide, or you know, common to be you know, just under 2 feet, like you know, 18 inches or something like that. And so if we're on 18 inches and we're on top of a plywood substrate, our uplift force it can be it can be based on what the substrate is, based on the strength of your panel, based on how wide that panel is, you can get substantial weakening ratings on that panel. So if I'm on 1/2 inch plywood on an 18-inch on center metal roof, my uplift force is only 53 pounds. You know, that's not even enough for a 4-foot on center attachment. I might have to go to a 2-foot on center attachment for that. And these attachments do cost a decent amount. You know, I did a off-grid standing seam metal rooftop project recently where we were using all black modules. So we bought these clips and then we had to send them to a metal shop to get them black anodized so that they would match the color. Ended up looking really good, but it turned out that the cost of that all in was there wasn't really much savings on getting rid of the rail because the amount of clips you have are now, you know, twice as much as what you would on 4-foot on center. So you're buying so many clips and then you have to install all of the clips. And this was a 22 kilowatt array where we're putting a clip on every single seam. You know, it was kind of annoying, lots of clipping, but you had to, you know, because of your pull strength. And I think that that's a common mistake. You read the manuals for standing seam metal roof racking systems, and they tell you to put a clip on every single seam. You know, when I'm doing Versa brackets and I'm going into the purlin, that's a much stronger attachment that goes directly into the rooftop. So that's when I'm going back into, you know, 4-foot on center staggered. Now, flat roofs, like commercial flat roofs, boy, that put hair on my chest when I had done, you know, 40 residential arrays, and then all of a sudden you get a commercial project that's twice as large as all of your previous work experience. And the last thing you want to do is go to a commercial building owner and say, we're going to make Swiss cheese out of your rooftop. You know, maybe the commercial flat roof is already leaky. So putting solar on it might exacerbate the problems. Well, the racking companies came up with, they borrowed a page from the satellite industry and they said, we're gonna fill this all in with concrete. And we're not going to have any penetrations. The array will just sit flat on top of the rooftop. Well, these concrete ballasted systems, you know, can weigh up to 8 pounds a square foot. Whereas the penetrating solar will weigh 3 pounds a square foot at the residential level. If you're building a little undercarriage for the array, that might be, this array was 4 pounds a square foot versus 8. All right, well, let's say they're the same weight. Let's say you don't have to put concrete all across the array, but strategically located at the edges and the corners, and then less weight in the interior, and that reduces the weight so that the building can take it. Oh, what if your building burns down? Now you have all these, like it did in the Dietz Watson warehouse fire. There were reports of the fire department showing up, and they see the solar array that's burnt a hole through the roof, and they see concrete blocks falling through the rooftop. Now, that's a safety hazard for any fireman. They said we could not go in that building to fight the fire, and the whole warehouse burned down because of that. I would hate to have, the fire might not be the solar array's fault. It was in that case, but it might not be. In that case, they didn't plan for expansion joints. And so your copper wiring and your metal conduit expanded at different rates, frayed into your home run conductors, and then they had an old style inverter that has a blind spot in it, and it just hit that blind spot correctly to the point where it started this fire, and then that added weight causes additional problems. Why add the weight if you don't need it? That's dangerous. As a structural engineer, you should think that might be unethical. Well, the solar installer that doesn't have any roofing experience certainly doesn't have any commercial roofing experience. So the last thing they want to do is poke a bunch of holes in a flat roof, especially when you go on these flat rooftops. Not all the water makes it to the drain. So on these flat roofs, you can get lakes of water on the array. Now, these ballasted systems only sit like an inch above the roof deck. So putting a system that's only 1 inch above the roof deck on a roof deck will accumulate water, that's not a very good idea either. I like elevated ballasted systems. It was actually pretty interesting. When you're on a slanted rooftop and you put your array up on top of a slanted rooftop, if you don't attach it, it's going to fall off. If you put an array on top of a commercial building and you don't attach it, it's going to sit there until there's an extreme weather event, like a nearby tornado or windstorm or whatever. And so the penetrations on a residential array are for anchoring the array to the rooftop. Gravity anchors the array to the roof on a commercial array, whether it's 8 pounds or 4 pounds. And so if it's a lighter weight array on a commercial project, you essentially just anchor the corners of the array rather than every single foot. So these are just little conduit supports that we're using to elevate our racking. And then at the edges, you see this pipe boot. And so we've gone and bolted into our iron rafters and then tamped down the TPO membrane. When I say we, I meant the roofing contractor that was in the area for this roofing system came out and did the pipe boot sealing. And this is actually on a TPO roof. You kind of use a heat gun and melt the flashing onto the TPO roof where it adheres, and it forms a very watertight seal. And so when all was said and done at the end of this project, we had poked fewer holes in the rooftop than what the air conditioning system had done. Solar's not the only thing that pokes a hole in a roof. They have leaks because of the drains. Where the drains go, that's a hole in the roof, and those drains leak. And so is this solar hole going to leak? No, it's new, it's welded, it's flashed, it's done in a workmanlike manner. It's going to be great. And so the difference was by putting like 1 out of every 40 supports was anchored to this building. It might have even been a bigger ratio than that. By putting a scant number of penetrations into that rooftop, we were able to reduce the weight of the array by half and get the concrete off of the roof which is a much safer design. It's a cheaper design. It's a better design structurally. The solar installer who knows nothing about roofing or structural engineering is going to go with the worst design. In fact, this racking system that we used, it's a pain in the butt to install. It's very difficult, heavy, not fun for your labor. But you do it once, and you get it done. This blocking system, I'm not a fan. Well, we went to go and expand the array, and we bought the next section of the racking, and our racking supplier said, y'all are our last customer on this racking system. He said, what do you mean? And he said, well, we're discontinuing it because all of our installers want to buy this stuff and not this stuff. This stuff costs half the price because it's half the metal. So the solar installer is choosing a cheaper system that doesn't have any penetrations. I can easily understand why a building owner would say, I'm going to go with that solar installer who knows what they're doing because it's cheaper and I don't have to worry about roof leaks. That would be the wrong decision to make. And just kind of some interesting things about reinforcing the roof. This is not a solar project, but this is what they do in Florida to make hurricane-proof homes is take the decking and then glue it to the rafters. That gets complicated if you ever have to, replace the rooftop. You have to like saw through that. Then again, if I have 3 purlins and I'm using a shared rail system, and I know that middle purlin is going to have twice the load it normally does, I might get in there and glue some additional wood members to where that rafter and decking interface to give it a little bit more cohesive strength. If I'm using a decking-based racking system where I'm going into this surface board, at that point I may go and reinforce the board to the truss underneath. So that's kind of I've never actually seen anyone do this. This is when I found kind of researching decking-based racking systems on how to better secure the decking or the cladding to the truss. We talked about this yesterday. So here's a ground mount we built for Half Moon residential. Most solar installers will tell you that ground mount is way more expensive than roof mounting. I'm like, well, you have to do all the foundation work for a ground mount. Now you don't have to do on a rooftop. Okay, but you're still buying the rail. You're still buying the clips. In fact, those clips, those flashed L feet are pretty expensive comparatively, and you're not buying that. Well, you are buying this additional rail. So this additional support beam right here is about the same cost as buying flashed attachments. And so really the only additional cost for doing a ground mount is digging out the foundations and the cost of the concrete, which is not terribly expensive. I mean, I built this kind of frame with a post hole digger and some quickcrete and some electrical metal products. It was like $500 for a 4 kilowatt system, about 20 cents a watt or so. And in fact, some of your utility scale racking companies are now kitting out their utility scale racks to the residential market. And so for us, it was as simple as, we're doing a ground mount. So we're going to rent a trencher for this trench from the array back to the point of interconnection. Well, we're already paying a delivery fee for the trencher, and so we're also going to rent a bobcat so that we can move some equipment around and have it be delivered with the trencher. So the trencher and the bobcat show up. One of our electricians runs the trench, the other electrician's digging out these. We rent a auger attachment. These are about 6.5 foot deep foundations. And the nice thing is you're no longer on the rooftop. It's much quicker to install on the ground than it is up on the roof. It's much safer to install on the ground than it is up on the roof. The maintenance is there. I mean, there's great reasons to go on the roof too, but the thing that I have found is that general contractors, when they do a ground mount, even if they have to dig a 20-foot trench, they're going to want to rent a trencher because they know that the trencher is going to offer a better value than paying their labor to dig it out. So if you're handy with construction equipment, your ground mount pricing can be quite competitive. I would price a ground mount to be the same as a residential mount simply because I don't like getting up on the roof. If they have the space to go on the ground, I'd rather keep the project much more simple by having it stay on the ground. So it used to be that the ground mount racking did not exist, or what did exist was very expensive. I mean, if you're talking about doing a Schedule 80 pipe that's 6 feet out of the ground and 7 feet into the ground that can hold a giant elevated 200 square foot solar array, then yeah, that's absolutely going to cost you 5 times as much as a residential racking system. But the utility scale racking system, we've seen the numbers. It's right in line with the residential racking cost. Now, this is kind of too advanced for a intro class, but one thing that I think is fascinating is that while the modules are designed to plug into their next door neighbor, positive, negative, positive, negative, positive, negative, those slightly taller 72 cell modules, your module whips are designed so that they can be mounted in portrait, but also in landscape. And so you take these taller 72 cell modules, and the module whips are actually long enough so that you can plug them into every other neighbor rather than your next door neighbor. And what that allows you to do is get to the end and then come all the way home. And so you're actually using your cable whips as your home run circuit, and that improves efficiency and also slightly reduces material costs. Now that's kind of being a little bit too much overthinking, but you can find the dimension of your cable width on your module spec sheet if you really want to look into it. So this was an experiment. Half Moon came to me and they said we have $15,000 to do a solar project at the residential home. I looked at their electric bill and I said, well, that's not enough to take you off grid, but let's do as much solar as we possibly can today with an eye towards taking your home off grid in the future. So I used a multiple PowerPoint tracker. I did 3 strings of 8. That was 24 modules. That was very intentional because the ground mount kit could hold 12 modules each, and the pallet of 72 cell modules comes with 25 solar modules in it. And so instead of designing for the roof, doing a custom design, we could optimize our purchasing quantities, get exact, the racking didn't need to be customized. It's just, hey, give me that kit. It's 1 pallet of modules. Who cares that there's an extra solar module? Let's just take it and do something fun with it. And here's our array layout, our 1-line diagram. All this documentation is computer generated. So this is Solar Design Tool. And while it's not perfect, it will do things like after you tell it the size of your, it'll tell you the minimum cable sizes. And then you might go in and say, okay, well, I'm using number 8 here and number 10 here. And so I'm going to go and check my inverter terminals to make sure they can take number 8. And at that point, I might just upsize all of my cable to number 8 so that I'm not dealing with multiple conduit sizes, multiple cable sizes, just to simplify the install. Now, what I've done is this project was installed. This one was installed in 2016. Pricing hasn't changed too much. Modules have gotten cheaper, but the import tariffs have increased. They've kind of offset each other. So we use a very high-end SMA inverter. So these are the actual project costs of our racking, our inverter, our cable. We actually bought twice as much cable as we needed because when we were doing that trench, we went ahead and ran double the amount of home run conductors so that they could expand the array later if they wanted to go off grid. And so spending an extra, $170 on cable was all that we needed to make the array solar ready for expansion. So we won't have to rent that trencher and potentially dig a new trench adjacent to our existing trench down the line. So our total material cost was 11 grand. We spent about 300 bucks, 400 bucks on concrete, $2,000 in labor for two $75 an hour electricians to come out for 2 days to install the array. Union electricians, one was a master, one was a foreman. They had heavy equipment experience, no muss, no fuss, no getting on the rooftop. Maybe their insurance isn't for roof work. Roof work is the highest craft insurance that you can buy out of your mainstream craft laborers. Throw in the equipment rental, throw in a design fee. I went up to help with the install. I kind of gave Half Moon a sweetheart deal because they have me for classes. We went a little over budget, $17,000, 24 modules at 310 watts. The ground mount project costs $2.27 a watt. Now, a lot of rooftop solar is being bid at over $3 a watt. This didn't include any profit margin. If I put a 30% margin on top of that, then I'm right up at $3 a watt for a 3-day, including inspection, ground mount system. Cool. So I put in actual material cost for future reference. We're kind of getting close to the end of time, so not going to spend as much time on these slides as others. Now, what we did is we just installed the solar inverter with the solar array out in the field. But we selected an inverter whose battery manufacturer has a battery inverter. And the reason being is you don't need your solar inverter and your battery inverter to be of the same brand. The same grid protections that are built into your grid protected inverters that'll shut down the inverter during a power outage. If you take that with a battery and a battery inverter and you have a transfer switch so that this will be an off-grid array when there's a power outage, the danger is that if your batteries are full and your solar's at full power, potentially you could be backfeeding the batteries over voltage and damaging them. And so what your battery inverter will do is it'll shift the frequency of your electricity from 60 hertz to 58 hertz. And that'll trigger the shut-off protection in the solar inverter independent of what manufacturer it is. And so you can just get the cheapest solar inverter that's batteryless today and then add a battery inverter of a different manufacturer tomorrow and they'll be compatible. But what that means is there's going to be times when you're turning off your array and then cycling your battery down and then recharging that battery back up. Wouldn't it be better to not use the battery and just draw the power from the array? The advantage of keeping everything in the same product line is that they can communicate with each other so that the battery inverter, instead of turning the solar array off, it can just tell it to, hey, let's dial back your production rather than turning you completely off. So it can do a little bit better load balancing if you stay within the same product line. So, we selected an inverter because they had a battery roadmap. Kind of the last thing that's very important for class is, where do you interconnect the array? Do you interconnect it on your service panel? You have two choices. You can do a load side connection, which is interconnected to your service panel, or you can do a supply side connection. Now, if you go into a load side connection where you're going into your service panel is a 200 amp panel, and it's being fed by 200 amps from the utility. And so if I'm back feeding it with solar, I have a 200 amp feed from the utility, a 200 amp panel. If I back feed it with additional power, I'm going to exceed the power rating of that panel. Now, National Electric Code allows you 20% additional amperage, provided that the solar array actually lands on the opposite end that the utility feed is tied into. But regardless, if you do a load side interconnection, you can only use 20% of the panel's rated amperage. Then again, the power lines that are going into the building, and this is a heat pump on a separate service, so just ignore that. But the power going into the building, that's rated for 200 amps because it's feeding a 200 amp panel. And so instead of, this is the box where we're going into the service panel that's on the other side of the building, or on the other side of that wall. And so our cables that go into the building are actually rated for 200 amps. And what that means is I can put a box between where the power comes in from the utility and where it goes into the service panel. It's still on the customer side of the meter, but it's on the utility side of the main service panel. And at that point, I don't need to do 20%, I can do 100%. And that's because whether the power comes from the utility or the solar array, under no circumstance would the power exceed 200 amps. And so I really like what are called supply side taps, where you go into the conductors before they go into the building, because then you can do 100% of the rated capacity. Now, 20% of the rated capacity, that's a 40 amp breaker on a 200 amp panel. Well, 40 amps times 240 volts, that's about a 8 to 9 kilowatt solar array. And that's, in most circumstances, going to be enough to offset your electric bill. And so for many residential installers, they'll just go and do a load side connection, mainly because they'll work the service panel hot, even though they really shouldn't. Especially at the residential level, the utility will come and turn off your power for free if you're doing electrical work. But it's lazier to work the panel hot, and they're going to do that. On a line side connection, you have to actually get the utility come out to turn out the power so that you can open this up and tap onto it. But the thing is, if you do a solar array to offset most of your client's bill and you use that 20% amperage that you have, what happens down the road when you want to add a battery? What happens down the road if you might have a different supply, like a charger for an electric vehicle? You're out of amperage. And so you're going to have to do a supply side tap anyway. And so where kind of electrical design is going is that there's actually going to be two service panels for a home. There's going to be an energy distribution panel, and maybe this is also a transfer switch that can take the home on and off the grid. And after you come out of the energy distribution panel, that's when what you would land on what we would consider to be our main distribution panel or main service panel. And that way you can always have as much power as you need to feed the panel. You know, most residential panels are not using 100% of their capacity at any time. They might be using 10% of their capacity at any time. So a solar array that produces twice as much power for 1/3 of the day can do damage onto the bill. All right, so we're approaching the end of our time. So here's some kind of lessons learned. The skip stepping really didn't improve anything. Going with 72 cell modules increased our racking cost by about $40, and it saved us $140 in terms of total project cost of being able to squeeze more modules onto the racking footprint. So 72 cell modules for ground mounting, big fan of that. I'm not a fan of, even if you're on a ground mount and you don't need to have a junction box out of the array before you go into the ground and come up the other side on your inverter, go ahead and put one in there, because it's just good to have a serviceable box out at the ground mount location, even if you're not required to by code. So we were able to get them down to a 9-year payback. Now here's the MC4 connectors we talked about earlier. Some pictures on that process of making it. This is like the #1 place that you're going to make a workmanship error, other than like squaring the array. I mean, this is more of the specialty skill. You have to take your time to make sure that these things don't slide around after you crimp them on. You want to make sure that the crimp holds. There's a specialty solar cable. It's just called PV cable. So it's not, PV for photovoltaic. So it's, basically it's a single conductor cable like THWN or something, but it's a thicker gauge cable. It has a thicker jacket. You really don't want to use solar cable inside of conduit, because it's that thicker jacket, clogs up your conduit and also has more heat. This solar cable is for outside of conduit, exposed to the elements. Not maybe direct exposure to sunlight, but it'll hold up to the outdoors. We have a class on National Electric Code. Out of the multiple classes I teach, it's definitely the one that I'm most rough at, but we cover in locations. But basically what you need to be careful of is if you're using flooded lead acid batteries, that becomes a corrosive environment. So you want to use a plastic wrapped conduit. Another thing that I'm a huge fan of, right here they're using flex metal conduit. DC cable has to be in metal clad or EMT when it's inside the building. What I will typically do instead is not use metal flex and EMT in the attic. I'll use metal clad cable called MC cable. And it's expensive. It's like twice as much, but it's all bundled already, and you can just strap it to the rafters and not need to worry about it so much. So we talked about how you can go onto the line side or the load side of the panel. On Half Moon's commercial array, we went with the line side because we didn't want the inspector coming in here. There's a couple of code violations going on and workmanship conditions that we just wanted to not have the inspector come in and see. So this was the scope we wrote. The electrician came out before the install, cut power to the building, pulled the cables out of where they go into the building onto these 2 service panels, and then we installed a junction box where this LB is and landed our solar service panel right there. So here there's the junction box, our service panel, and our supply side tap. These are different tap products that you can use, but generally I would warn you against insulating piercing tap conductors versus traditional taps. These are made for doing hot, but these electricians I've talked to, they have doubts about the fire safety of this, because your conductor jacket is still right in there. So if it heats up and it's not supposed to, it could smolder the jacket and potentially start a fire. And with this, we're kind of at the end of our time. And so since we cover a lot of this stuff in the National Electric Code class, I'll just tell you that the #1 error that I see seasoned installers making is wherever your conduit is going from underground up to into a box, or like from the attic up to the rooftop, you have to put sealant inside the conduit to make that, relatively airtight. Because otherwise the humidity in the air with the temperature differential between the attic and the rooftop, or the ground and the above ground, it'll cause the humidity in the air to rain inside your box. So you can have a completely weatherproof box that's not completely airtight, and you'll still get moisture inside the box just because of humidity and temperature differential. So spraying in some sealant inside that conduit is now part of code. And with that, batteries are on the rise. We have a battery class. Demand rate structures are now economic. We talk about that in the battery class. And so here's some slides from the battery class. If you want additional course material and course recordings, go ahead and join the Slack community or send me an email. I'll put my email address right in here. My website, you can also contact me that way. I prefer email or contact forms. Online resources, definitely check this website out. It's desireusa.org. It covers what your net metering policy is and what your interconnection policies are, what your insurance requirements would be, and what if there's any sales tax exemptions. About 20% of the U.S. has sales tax exemptions. I think it's a good policy because a lot of mainstream power plants get sales tax exemptions. So, let's have policies that don't make businesses to be better than people. But you can get all this information starting at the Desire website. Solar Pro is a great magazine if you want to professionally learn about solar, if you're interested in being a contractor. Home Power is a little bit better if you're more of a residential enthusiast. Same company. NABCEP, if you want to find an installer, that's where you go. That's the solar trade organization I'm in. It's not a union. It's more like the U.S. Green Building Council, but for solar. And it used to be used as a certification requirement for rebate programs. I think as we've bucked rebates, it's become more of a quality indicator, and I think that's a better application for it. A lot of this other stuff we're just going to talk about in the battery class. We just can't cover it in 6 hours, but it is possible if your electric policy is very punitive against solar to take the home off grid during the day and reconnect to the grid at night. We're in the very early stages of designing an off-grid system for an office building. The homeowner already lives off-grid, and he says, well, my office, I don't use my office at night, so I could take the same $80,000 off-grid residential array that I'd say is luxury residential, where he never has to worry about his electricity. That same system could take his whole office building off-grid and just not even deal with a grid connection. I don't know if that's cost effective or not, but this particular client really likes solar, and he understands that his utility policy is very anti-solar, and so he'd rather invest in his own building and not support his electric cooperative. So this stuff we talk about in the battery classes. Other than that, we're just out of time. So if you want more, take more classes or send me an email, join the Slack community, and but other than that, we're out of time. I'm going to pass it back to Half Moon, and